Subscribe to the channel so you don't miss out on any of these videos. The fabric of the universe, the endless dance of stars, galaxies, and planets, is underpinned by something so small you can't even see it: protons. These tiny particles form the very foundation of the matter around us, from the air we breathe to the stars that light up our night skies. But what if I told you that these building blocks of reality, the things we thought were indestructible, might not last forever? What if protons could decay? This isn't just a wild sci-fi idea, it's a legitimate scientific hypothesis, one that could rewrite everything we think we know about the universe and its future. Imagine this for a moment: the matter in your body, your desk, the earth beneath your feet, it all just fades away. Not in an instant, but over incomprehensible stretches of time. It's an unsettling thought, right? It's like realizing the seemingly unshakable foundation of your home has cracks running through it, cracks you can't fix. The Proton Decay Hypothesis takes this unnerving idea and puts it under the lens of science. It suggests that the universe itself is in the process of unraveling, and the glue holding matter together could one day fail. This isn't just about protons. This is about the ultimate fate of everything. If protons decay, it means that, given enough time, the universe will be stripped of all matter. Only a cold, empty void would remain, a cosmic graveyard where even atoms cease to exist. It's the kind of mystery that raises goosebumps, and today, we're diving deep into what this all means. To grasp the weight of the proton decay hypothesis, we first need to understand what a proton actually is. Protons are subatomic particles nestled inside the nucleus of every atom, alongside neutrons. They're positively charged and serve as the building blocks for the chemical elements. For a long time, scientists believed protons were stable, that they'd last forever. After all, why wouldn't they? Everything in our everyday lives depends on their permanence. But as physicists began peeling back the layers of the quantum world, they stumbled upon a shocking possibility: protons might not be eternal. This idea isn't baseless speculation. It emerges from theories that aim to unify the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into one grand framework. The Standard Model of particle physics, which explains a lot about how particles interact, doesn't demand proton decay. However, extensions to this model, particularly grand unified theories, GUTS, suggest otherwise. These theories propose that, over mind-boggling timescales, protons might break down into lighter particles like positrons and neutrinos. But how long are we talking here? According to the most optimistic estimates, the half-life of a proton, meaning the time it takes for half the protons in a given sample to decay, is at least years. That's an unimaginably long time, far longer than the current age of the universe, which is a mere 13.8 billion years. If proton decay is real, it's happening on timescales so vast that it's practically invisible to us. And yet, the implications are enormous. Physicists have been hunting for evidence of proton decay for decades. Deep underground laboratories, shielded from cosmic rays and other sources of interference, house enormous tanks of water or liquid scintillator to catch the faint signals of decaying protons. One such experiment is the Super Kamiokande detector in Japan, which sits over 1,000 meters below ground. These experiments haven't detected definitive evidence of proton decay yet, but the absence of proof doesn't mean the hypothesis is wrong. It just means the process might be even rarer than we currently estimate, or that our understanding of particle physics is incomplete. So why does proton decay matter? For one, it forces us to confront the limits of the universe's longevity. If protons decay, the very structure of matter will eventually crumble. Stars would burn out as their nuclear fuel dissipates, planets would disintegrate, and black holes would be among the last remnants of the cosmos. The universe would drift into a state of maximum entropy, a scenario known as the heat death. It's a chilling reminder that even the cosmos isn't immune to the passage of time. But there's another layer to this mystery. The search for proton decay isn't just about predicting doom and gloom, it's about uncovering deeper truths about the universe. If we find evidence of proton decay, it would provide a crucial link between quantum mechanics and cosmology. It would offer clues about the conditions of the early universe, when the fundamental forces might have been unified. In other words, understanding proton decay could bring us closer to answering some of the biggest questions in science. Why is there something rather than nothing? What are the ultimate rules governing reality? The idea of proton decay also ties into the concept of baryogenesis, which seeks to explain why the universe has more matter than antimatter. If protons can decay, it suggests asymmetries in the fundamental laws of physics that might also explain why we live in a universe filled with stars and galaxies rather than one annihilated by its own reflection. For now, though, the proton decay hypothesis remains just that, a hypothesis. But it's a tantalizing one. It challenges our assumptions about permanence, and forces us to think about the far future of the universe in ways that feel almost philosophical. What does it mean for existence itself if everything we know will one day dissolve into nothingness? And yet, even in this potential end lies a kind of beauty. The search for proton decay is a testament to human curiosity, our relentless drive to understand the universe, no matter how uncomfortable the answers might be. It's a reminder that science isn't just about solving problems, it's about exploring the unknown, no matter how unsettling it might be. This exploration of proton decay isn't just about the distant future of the cosmos, it's also deeply intertwined with how we understand the origins of the universe itself. To grasp this connection, we need to look back at the earliest moments after the Big Bang. In those first fractions of a second, the universe was an unimaginably hot, dense soup of energy. Matter as we know it didn't exist yet. Instead, fundamental particles were being created and destroyed in a chaotic dance. Eventually, as the universe cooled, these particles began to combine, forming the protons and neutrons that make up atomic nuclei. If protons are capable of decaying, it raises profound questions about this formative period. Could proton decay have played a role in shaping the distribution of matter and antimatter? Could it have influenced the creation of elements, or the conditions that allowed galaxies to form? These are the kinds of questions that keep physicists up at night. And the potential answers could reshape our understanding of how everything, literally everything, came to be. Now, let's step back and consider the practical side of searching for proton decay. Scientists are incredibly patient people. They have to be, especially when hunting for phenomena that occur over timescales much longer than human lifetimes. Experiments like Super Cameo Candy don't just run for weeks or months. They're designed to operate for decades, collecting data in the hopes of capturing even the faintest hint of a proton breaking down. The detectors used in these experiments are marvels of engineering. Imagine a massive underground cavern filled with tens of thousands of tons of ultra-pure water. Surrounding this tank are thousands of sensitive light detectors, designed to pick up tiny flashes of light caused by particles interacting with the water. If a proton were to decay inside this setup, it would produce specific particles that would leave a telltale signature. Catching that signature is the challenge, and so far, nature has proven elusive. But the lack of direct evidence doesn't mean the hypothesis is without merit. In science, absence of evidence isn't evidence of absence. What's fascinating is that the limits placed on proton decay by these experiments are themselves incredibly informative. Each failed attempt to observe proton decay pushes the estimated half-life of protons even higher, refining our understanding of the universe's stability. Let's talk about the implications of this stability. If protons really don't decay, it would mean that matter, as we know it, could essentially last forever. That's comforting on one level. It suggests that the universe might have an eternal foundation. But it also raises questions about the ultimate fate of the cosmos. Without proton decay, the universe might never reach a state of total emptiness, but it could still drift into a kind of lifeless stasis, with cold, dead stars and ever-expanding voids. Either way, the long-term outlook isn't exactly cheerful. The proton decay hypothesis also connects to other profound mysteries, like the nature of dark matter. Dark matter is an invisible form of matter that doesn't emit or absorb light, yet it exerts gravitational forces and makes up most of the universe's mass. If protons decay, could dark matter particles be stable remnants of this process? Or could the mechanisms governing proton decay provide clues about the mysterious properties of dark matter? These are speculative questions, but they highlight how interconnected the puzzles of physics really are. On a more philosophical level, the concept of proton decay forces us to confront the impermanence of everything we hold familiar. Human beings are wired to think in terms of stability and permanence. The idea that something as fundamental as matter could vanish is deeply unsettling. But it's also a humbling reminder of our place in the universe. We're fleeting inhabitants of a cosmos that operates on scales of time and space far beyond our comprehension. As we dive deeper into the physics behind proton decay, it's worth mentioning that the search itself isn't just about answering questions, it's about asking better ones. Each experiment, each theoretical breakthrough, opens up new avenues of inquiry. Even if we never observe proton decay directly, the pursuit might lead us to discoveries we can't even imagine yet. This is the beauty of science. It's not just about finding answers, but about expanding the boundaries of what we know and don't know. There's also a poetic irony in the idea of proton decay. For centuries, human beings have sought permanence, something unchanging and eternal to anchor their understanding of the world. Yet science repeatedly shows us that change is the only constant. Stars are born and die. Galaxies collide. Even the universe itself evolves. If protons do decay, it would be the ultimate affirmation of this truth, that nothing, not even the most fundamental particles, is immune to the passage of time. And yet, this isn't a cause for despair. The impermanence of protons, if real, doesn't diminish the wonder of the universe. On the contrary, it amplifies it. The fact that we can even ask these questions, that we can use our finite lives to study the infinite, is a testament to the resilience of human curiosity. Whether or not protons decay, our quest to understand the universe continues. It's a journey without a final destination, but that's what makes it so extraordinary. The journey to understand proton decay isn't just a scientific endeavor. It's a testament to our ability to imagine possibilities that lie far beyond what we can see or measure. At its core, the proton decay hypothesis is about peeling back the layers of the universe's hidden mechanics, revealing a reality that is both beautiful and deeply unsettling. Let's dive further into the implications of proton decay and why this concept matters on a cosmic and human scale. To appreciate the broader significance of proton decay, we need to revisit the standard model of particle physics. This framework is like a guidebook for understanding the universe at its most fundamental level. It describes the interactions between elementary particles, the smallest known building blocks of reality, and the forces that govern them. However, the standard model isn't perfect. While it has accurately predicted many phenomena, it doesn't account for gravity or fully explain the asymmetry between matter and antimatter in the universe. This is where grand unified theories, GUTs, and theories of everything TUEs come into play. Proton decay is a cornerstone prediction of many GUTs, which aim to unify the strong nuclear force, weak nuclear force, and electromagnetic force into a single, cohesive framework. According to these theories, the forces we observe today were once part of a unified force in the extremely hot, dense conditions of the early universe. As the universe cooled, this symmetry broke, and the forces became distinct. Proton decay, if observed, would be a tangible clue that these forces were once unified, a glimpse into the universe's earliest moments. This brings us to the connection between proton decay and quantum mechanics. At the quantum level, particles don't behave like solid, unchanging entities. Instead, they exist as probabilities, constantly fluctuating and interacting. Proton decay, in essence, is a quantum process. It involves a proton transforming into lighter particles through a process mediated by hypothetical particles predicted by GUTs. These transformations are incredibly rare, so rare, in fact, that they might only occur once in a proton's lifetime of years. But the mechanisms behind this decay could unlock secrets about the very fabric of spacetime. If protons decay, it could also help explain the apparent scarcity of antimatter in the universe. When the universe began, matter and antimatter were produced in almost equal amounts. Yet today, the cosmos is overwhelmingly dominated by matter. Where did all the antimatter go? Proton decay might be tied to this imbalance. Certain GUTs suggest that the same processes responsible for proton decay could have created a slight preference for matter over antimatter in the early universe. This tiny asymmetry would have allowed matter to survive while most of the antimatter was annihilated, leaving behind the stars, planets, and galaxies we see today. But let's zoom out and consider the cosmic implications of proton decay. If it's real, then the universe is fundamentally unstable. Over unimaginably long timescales, the matter that makes up stars, planets, and even black holes would eventually disintegrate. The result would be a universe devoid of structure, with only radiation and subatomic particles remaining. This scenario is part of what physicists call the heat death of the universe, a state where all energy is evenly distributed and no work can be done. While this might sound grim, it's important to remember that this process would unfold over an almost incomprehensible amount of time. Even if proton decay is happening, it's so slow that the universe would still have many trillions of years before its matter begins to noticeably degrade. In the meantime, stars will continue to shine, galaxies will continue to evolve, and life, as we know it, will continue to exist. Now, let's bring this back to the human perspective. Why should we care about proton decay, a phenomenon that might never affect our daily lives? The answer lies in the fundamental nature of science itself. Proton decay isn't just about understanding particles, it's about understanding the universe and our place within it. The fact that we can even conceive of such ideas, let alone design experiments to test them, speaks to the incredible ingenuity of the human mind. Moreover, the search for proton decay represents a bridge between the known and the unknown. It challenges us to think about the universe in ways that transcend our everyday experience. It invites us to grapple with questions that have no easy answers, questions that force us to confront the limits of our knowledge and imagination. In doing so, it reminds us that the pursuit of truth is a journey, not a destination. Proton decay also has profound implications for the future of science and technology. If we can confirm its existence, it would validate many of the theoretical frameworks that physicists have been developing for decades. This, in turn, could pave the way for new breakthroughs in our understanding of the cosmos. It might even lead to practical applications we can't yet envision, much like how quantum mechanics gave rise to technologies like semiconductors and lasers. But perhaps the most compelling reason to study proton decay is that it represents the ultimate mystery, the question of why the universe is the way it is. What are the rules that govern reality? Are they immutable, or are they subject to change? And if they can change, what does that mean for the future of existence itself? These are the kinds of questions that inspire awe and wonder, the kinds of questions that make us feel both small and infinitely connected to the cosmos. The proton decay hypothesis isn't just a scientific idea, it's a reminder of the fragility and beauty of the universe. It's a call to curiosity, a challenge to explore the boundaries of what we know and venture into the unknown. Whether or not protons decay, the pursuit of this mystery enriches our understanding of the cosmos and our place within it. The proton decay hypothesis also compels us to think about time in a way that stretches far beyond our usual comprehension. Humans measure time in seconds, minutes, hours, and years, scales that are minuscule compared to the grand timeline of the cosmos. But when discussing proton decay, we must grapple with timescales that are almost incomprehensible, trillions of years, or even longer. These immense spans of time force us to confront the transient nature of our own existence against the backdrop of a universe that endures far beyond our ability to witness or measure directly. Even if protons were confirmed to decay, this process would unfold so slowly that it wouldn't impact our day-to-day lives. The universe would remain hospitable for countless generations to come. Still, the very possibility of proton decay forces us to reckon with the idea that the universe itself may not be as eternal as it seems. This notion adds an existential dimension to the study of physics. It's not just about understanding the fundamental particles but also about grasping the eventual fate of everything built upon them. Another fascinating layer to the proton decay hypothesis is its connection to theories of the multiverse. If protons can decay, it might suggest that the physical laws governing our universe are not immutable. They could be specific to our universe's unique configuration and might differ in other possible universes. This raises the tantalizing possibility that proton stability, or instability, could vary across different universes in the multiverse. Could there exist parallel universes where protons decay much faster or not at all? If so, what would such a universe look like? These speculative questions illustrate how a single phenomenon like proton decay can ripple outward, touching on some of the deepest mysteries of reality. The hunt for proton decay also ties into the concept of symmetry in physics. In the natural world, symmetry is often seen as a sign of beauty and simplicity. The Standard Model relies heavily on symmetrical principles to explain particle interactions. However, the existence of proton decay would indicate a slight violation of certain symmetries, such as baryon number conservation. This violation is significant because it points to deeper, hidden principles governing the universe. It's as though proton decay is a tiny crack in the facade of reality, hinting at something more profound lying beneath. As physicists probe the proton decay hypothesis, they must also wrestle with the limitations of human observation. The immense timescales involved make it nearly impossible to directly observe a proton decaying. Instead, scientists rely on statistical methods and indirect evidence, such as searching for the particles that would result from proton decay. This indirect approach has parallels in other areas of science, such as the study of dark matter or black holes, where direct observation is equally elusive. These methods highlight the ingenuity of human beings in uncovering truths about phenomena we cannot see but can infer through their effects. The philosophical implications of proton decay are equally profound. If protons are destined to decay, it suggests that even the most fundamental components of matter are impermanent. This challenges the deeply ingrained human notion that some things are unchanging and eternal. It raises questions about the nature of existence itself. If even protons cannot last forever, what does that say about the ultimate fate of the universe? Is everything we know and cherish ultimately destined to fade into oblivion? While these are unsettling thoughts, they also underscore the fleeting beauty of the cosmos and the importance of cherishing the time we have. Interestingly, the study of proton decay could also influence our understanding of entropy and the second law of thermodynamics. As protons decay over vast timescales, the universe's overall entropy would increase, pushing it closer to a state of maximum disorder. This ties into the heat-death scenario, where the universe reaches thermodynamic equilibrium, rendering it lifeless and inert. Proton decay might serve as one of the mechanisms driving this long-term increase in entropy, making it a key player in the cosmic narrative of decline and transformation. But let's consider the counterargument. What if protons do not decay? If experiments continue to push the lower bounds of proton half-lives to greater and greater values without finding evidence of decay, it might suggest that protons are truly stable. This would have equally profound implications. A stable proton would mean that matter could exist indefinitely, creating a universe that might never fully dissolve into radiation and emptiness. While this scenario might seem more optimistic, it still leaves unanswered questions about the ultimate fate of the cosmos. Even if protons last forever, the universe itself might still face a slow and inevitable decline due to the expansion of space. The search for proton decay also highlights the interplay between theory and experiment in science. On the theoretical side, grand unified theories predict proton decay as a natural consequence of their frameworks. On the experimental side, physicists have constructed massive detectors and spent decades searching for evidence. This back and forth between theory and experiment is a hallmark of scientific progress. Even the absence of evidence for proton decay provides valuable feedback, helping to refine theories and guide future research. In some ways, the quest to understand proton decay mirrors humanity's broader quest for knowledge. It's a reminder that science isn't just about solving problems or achieving practical outcomes. It's about exploring the unknown, asking questions that may not have immediate answers, and pushing the boundaries of what we understand about the universe. Whether or not we ever confirm the existence of proton decay, the pursuit itself is a testament to the power of human curiosity and the desire to uncover the fundamental truths of reality. As we reflect on the proton decay hypothesis, it's worth remembering that this idea is part of a much larger story. It's a story about the origins of the universe, the nature of matter, and the ultimate fate of everything. It's a story that spans scales of time and space far beyond our everyday experience, yet it's also a story that connects us to the cosmos in a deeply personal way. The fact that we can even conceive of such questions, let alone attempt to answer them, is a remarkable achievement in its own right. The story of the proton decay hypothesis reminds us of the inherent duality in the quest for understanding, the beauty of discovery, and the daunting realization of what these discoveries might imply. On one hand, the potential evidence of proton decay could validate decades of theoretical work, provide the missing link for grand unified theories, and give us a more complete picture of the cosmos. On the other hand, it forces us to confront the fragility of existence itself and the possibility that everything we see and touch is ultimately fleeting. One particularly thought-provoking angle comes from the role proton decay plays in the concept of universal evolution. Just as stars are born, shine, and eventually die, so too might the very matter of the universe undergo a life cycle. In this grand view, protons may have formed shortly after the Big Bang, endured for eons, and may eventually decay into lighter particles. If this is true, then the universe itself could be viewed as a vast living system, undergoing phases of creation, transformation, and eventual dissolution. This poetic perspective invites us to consider the interconnectedness of all things, from the smallest subatomic particles to the largest cosmic structures. The search for proton decay also forces us to reconsider the scale of human significance. While this concept deals with phenomena that are far removed from human experience, both in size and time, it remains a uniquely human endeavor to explore such mysteries. The fact that we can hypothesize about events that might occur trillions of years into the future, using instruments and equations devised by human ingenuity, is a profound reminder of our capacity for intellectual exploration. It's a testament to the curiosity that drives us to ask not just how things work, but why they exist in the first place. Digging deeper into the science, the potential decay of a proton involves incredibly specific mechanisms dictated by quantum field theory. When a proton decays, it might transform into a positron and a neutral pion, which in turn decays into photons. The likelihood of such an event is vanishingly small at any given moment, which is why experiments must monitor enormous numbers of protons over long periods to have even a chance of detecting a single decay. This statistical nature of proton decay reflects a broader theme in quantum physics: the interplay between randomness and determinism. While individual events may be unpredictable, their aggregate behavior often follows precise mathematical laws. Another intriguing consideration is how proton decay might inform our understanding of the universe's earliest moments. Shortly after the Big Bang, the universe was a hot, dense soup of particles and radiation. During this time, the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single force. As the universe cooled and expanded, these forces separated, a process that might have allowed for the creation of protons and other particles. If protons are indeed capable of decay, it would suggest that the conditions of the early universe set the stage for their eventual instability, providing a direct link between the cosmos' beginning and its far distant future. The implications of proton decay extend beyond physics into realms like philosophy and even theology. For centuries, humans have grappled with questions about permanence and change, creation and destruction. The idea that even the building blocks of matter are impermanent challenges traditional notions of stability and eternity. For some, this might lead to existential unease, as it suggests a universe where nothing lasts forever. For others, it may inspire awe at the dynamism and creativity inherent in nature. The fact that the universe is constantly evolving, even at the level of its most fundamental particles, can be seen as a testament to the richness and complexity of existence. The proton decay hypothesis also brings attention to the collaborative nature of science. The experiments designed to detect proton decay, such as the Super Kamiokande detector in Japan, represent the work of countless scientists, engineers, and technicians from around the world. These detectors are marvels of human ingenuity, capable of monitoring vast numbers of particles with astonishing precision. They serve as a reminder that the pursuit of knowledge is not an individual endeavor but a collective effort, driven by the shared goal of understanding the universe. As we consider the potential reality of proton decay, it's important to remember the humility it inspires. The universe operates on scales of time, space, and complexity that far exceed our comprehension. Yet, through persistence and creativity, humanity has managed to uncover profound truths about the cosmos. Whether or not we ultimately confirm proton decay, the journey itself is a valuable reminder of our place in the universe, small but curious, transient but determined. The proton decay hypothesis is more than just a scientific idea, it's a window into the nature of existence itself. It challenges us to think beyond the immediate, to consider the ultimate fate of the universe and our role within it. It forces us to ask big questions. What does it mean for something to be permanent? How do we find meaning in a universe where even protons might not last forever? These are not questions with easy answers, but they are the kinds of questions that make life, and the pursuit of knowledge, so profoundly meaningful. The idea that protons may decay over unimaginable spans of time has broader implications that ripple across our understanding of cosmology, physics, and the future of life in the universe. To think of protons as unstable introduces a paradox of permanence versus transience, a fundamental aspect of reality that scientists and philosophers alike must grapple with. While we often think of the universe as composed of timeless building blocks, the possibility that even these elements may one day disintegrate forces us to reconsider everything we know about existence. On a cosmic scale, proton decay, if it occurs, could be the first domino to fall in the long, slow unraveling of the universe itself. In the distant future, long after stars have burned out and galaxies have dissipated, the decay of protons might mark the next phase of cosmic evolution. This scenario, often called the degenerate era, would be characterized by the breakdown of matter as we know it. Over incomprehensible timescales, larger structures like planets, stars, and black holes could evaporate or break apart, leaving behind a universe increasingly dominated by radiation and subatomic particles. This paints a sobering picture of the universe's future. But rather than viewing it as an endpoint, the concept of proton decay invites us to think about change as a fundamental process. If protons eventually decay, their constituent particles, such as quarks and leptons, may still persist, scattered across the vast expanse of the cosmos. These remnants could become the seeds of entirely new phenomena, perhaps even sparking forms of organization or complexity we cannot yet imagine. One fascinating aspect of the proton decay hypothesis is how it intersects with the anthropic principle, a philosophical argument that seeks to explain why the universe's physical constants are finely tuned to allow for life. The possible decay of protons introduces another layer of nuance to this principle. If matter itself is temporary, then life, and by extension, consciousness, exists within a fleeting, privileged window of the universe's lifespan. This makes the presence of life all the more extraordinary, a rare phenomenon arising in the brief moment when the cosmos supports stable matter. From a more practical perspective, the search for proton decay exemplifies the limits and ingenuity of human observation. Experimental physicists have spent decades refining their techniques, designing increasingly sensitive detectors that can monitor vast quantities of matter for faint signs of decay. These detectors, often buried deep underground to shield them from cosmic rays and background noise, are technological marvels. They are not just instruments but symbols of humanity's relentless drive to uncover the secrets of the universe, no matter how elusive or distant. The Super Kamiokande detector, for instance, uses a massive tank filled with ultra-pure water surrounded by thousands of light sensors. When a proton in the water decays, it is expected to release a burst of particles that can be detected as tiny flashes of light. Despite years of monitoring, no definitive evidence of proton decay has been found. Yet this lack of evidence is itself a critical result, pushing the estimated half-life of protons to greater and greater limits, now thought to exceed years. This staggering number underscores just how rare and slow the process of proton decay might be. The implications of this research extend far beyond the laboratory. If we were to definitively observe proton decay, it would validate some of the most ambitious and elegant theories in physics, including grand unified theories, GUTS. These frameworks attempt to merge the strong nuclear force, weak nuclear force, and electromagnetism into a single theoretical structure. Proton decay is one of the key predictions of these theories, making its discovery a potential breakthrough in our understanding of the universe's fundamental forces. Even the absence of evidence for proton decay has profound implications. It challenges physicists to rethink or refine their models, possibly leading to entirely new frameworks that explain why protons might be more stable than we currently expect. This iterative process of hypothesis, experimentation, and revision is the essence of scientific progress, showing that even negative results are valuable. In considering the proton decay hypothesis, it's also worth reflecting on the role of imagination in science. The concept of protons decaying over trillions of years is not something we can directly experience or observe in a traditional sense. It requires a leap of imagination, a willingness to think on scales of time and space far beyond human perception. This capacity to envision the unseen is what drives many of the most groundbreaking discoveries in science, from black holes to quantum mechanics. The philosophical dimensions of proton decay extend into questions of meaning and purpose. If everything we see and touch is ultimately transient, what does that say about the significance of human life and endeavor? For some, this might evoke a sense of existential futility. For others, it might inspire a deeper appreciation for the fleeting beauty of existence. The impermanence of matter can be seen not as a loss but as a reminder to cherish the present moment, to marvel at the complexity and wonder of the universe while it lasts. As we delve deeper into the proton decay hypothesis, it becomes clear that this idea is not just a scientific curiosity but a profound exploration of existence itself. It challenges our understanding of permanence, time, and the very fabric of reality. Whether or not protons decay, the journey to uncover the truth about them is a testament to humanity's unyielding quest for knowledge and our ability to imagine worlds far beyond our own. The exploration of the proton decay hypothesis is more than just a theoretical journey. It's a window into the nature of time itself. Imagine, for a moment, the concept of a proton half-life on the order of years. This is a timescale so vast that it dwarfs the age of the universe, which is a mere 13.8 billion years old by comparison. Trying to conceptualize such an immense stretch of time is nearly impossible, yet it's precisely this scale that researchers grapple with in their quest to understand proton decay. The very notion of a half-life implies that matter is not static but instead exists in a delicate dance with entropy and decay. Over time, this interaction could fundamentally reshape the structure of the cosmos. If protons do decay, the universe as we know it will change in ways that are difficult to fathom. Galaxies, stars, and planets, structures built from protons, could disintegrate into a sea of subatomic particles. This potential future challenges the common perception of the universe as a stable, enduring place. Delving deeper into the mechanics, the theoretical framework for proton decay stems from grand unified theories, or GUTS. These theories suggest that at incredibly high energy levels, such as those present in the early moments after the Big Bang, the electromagnetic, weak, and strong nuclear forces merge into a single unified force. This unification implies that certain processes forbidden by today's distinct forces, such as proton decay, could become possible under these conditions. In a simplified model, proton decay might involve the transformation of a proton into lighter particles, such as a positron and neutral pion. These particles would then rapidly decay into even simpler forms, like photons and neutrinos, leaving no trace of the original proton's mass. While this process sounds straightforward, the quantum mechanics underlying it are anything but. The phenomenon depends on incredibly rare quantum fluctuations that require vast amounts of matter and time to detect. The search for proton decay has pushed experimental physics to its limits. Instruments like the Super Kamiokande in Japan and the planned Hyper Kamiokande take advantage of cutting-edge technologies and massive scales. Super Kamiokande, for instance, monitors 50,000 tons of water using thousands of photomultiplier tubes to detect the faint flashes of light caused by rare particle interactions. The sheer scale and precision required to detect a single proton decay event demonstrate the ingenuity and ambition driving this field of research. Even though no definitive evidence for proton decay has been found, the experiments themselves have provided valuable insights. For one, they've set increasingly stringent lower bounds on the proton's half-life, refining our understanding of particle stability. Additionally, the same detectors designed to look for proton decay have contributed to other groundbreaking discoveries, such as the detection of neutrinos from supernovae and studies of neutrino oscillations. These findings highlight the interconnected nature of scientific inquiry, how one question can lead to answers in entirely different areas. Beyond the laboratory, the implications of proton decay extend to the universe's ultimate fate. If protons are unstable, the end of the universe might not be dominated by black holes or dark energy but by the slow dissolution of matter itself. This so-called proton decay era could last for unimaginable spans of time, with the cosmos gradually transforming into a thin soup of radiation and fundamental particles. Such a scenario paints a picture of a universe that doesn't end in a dramatic event but fades away in a slow, almost imperceptible process of decay. Yet, there's a certain beauty in this vision. It reminds us that even in the face of entropy and impermanence, the universe is a dynamic and ever-evolving system. Just as stars burn brightly before collapsing into black holes or neutron stars, so too might matter itself have a life cycle, a story of creation, transformation, and eventual dissolution. This perspective aligns with the broader principles of thermodynamics and evolution, suggesting that change and impermanence are fundamental aspects of existence. Philosophically, the proton decay hypothesis raises profound questions about the nature of reality and our place within it. If matter itself is not eternal, then what does that say about the human experience, which is already so brief by cosmic standards? For some, this realization might evoke a sense of insignificance. For others, it could inspire a deeper appreciation for the fleeting nature of life and the universe. The fact that we are here, able to ponder these questions, is itself an extraordinary occurrence, a moment of awareness in a cosmos that may one day become silent. The potential discovery of proton decay would also have implications for our understanding of time. In many ways, the concept of a half-life challenges our intuitive sense of time as linear and absolute. Instead, it suggests a probabilistic nature to existence, where stability is not permanent but a matter of chance over immense timescales. This perspective aligns with the broader principles of quantum mechanics, where uncertainty and probability play central roles. From a technological standpoint, the search for proton decay is a testament to human ingenuity and perseverance. Building detectors capable of observing such rare events requires not only advanced engineering but also decades of collaboration and incremental progress. It's a reminder that science is a cumulative endeavor, built on the contributions of countless individuals over generations. Even if the ultimate goal, detecting proton decay, remains elusive, the journey has already yielded valuable insights and innovations. As we reflect on the proton decay hypothesis, it's clear that this idea is about more than just particles and physics. It's a story about the nature of existence, the limits of human understanding, and the infinite curiosity that drives us to explore the unknown. Whether or not protons decay, the questions raised by this hypothesis will continue to inspire and challenge us, pushing the boundaries of what we know about the universe and our place within it. The potential for proton decay not only reshapes our understanding of the universe's far future but also forces us to re-examine the building blocks of reality itself. Protons are often viewed as fundamental, immutable components of atoms, the anchors of matter. The notion that these anchors might not be permanent adds an element of fragility to the cosmos, suggesting that even the most stable-seeming elements of reality are subject to the inexorable march of time and entropy. One fascinating implication of proton decay is its potential role in explaining the asymmetry between matter and antimatter in the universe. According to theoretical models, the early universe should have produced equal amounts of matter and antimatter during the Big Bang. However, our observations show a universe overwhelmingly dominated by matter, with antimatter being exceedingly rare. This imbalance, known as the baryon asymmetry problem, remains one of the great unsolved mysteries of cosmology. Some grand unified theories suggest that processes like proton decay could be connected to mechanisms that favor matter over antimatter in the early universe. If protons decay in specific ways, it might hint at a deeper symmetry-breaking process that allowed matter to prevail. Solving this puzzle would not only shed light on proton decay but also provide answers to one of the most fundamental questions about the origins of the universe. But even beyond its cosmological implications, proton decay holds profound consequences for the concept of permanence. Human history is marked by our attempts to create things that last, from the construction of ancient monuments to the preservation of scientific knowledge. Yet the possibility that protons might eventually decay underscores a stark reality. Nothing, not even the atoms that form our bodies or the structures we build, is truly eternal. Everything is subject to change, decay, and transformation over time. This realization can be both sobering and empowering. On one hand, it highlights the fleeting nature of existence. On the other, it reinforces the value of the present moment and the incredible resilience of life in a universe where permanence is an illusion. After all, life itself thrives on change, adapting to shifting environments, evolving over generations, and finding ways to endure in the face of entropy. The search for proton decay also illustrates the interplay between theory and experiment in science. Theoretical physicists use mathematical models to predict how protons might decay, drawing on concepts like symmetry breaking and quantum tunneling. Meanwhile, experimental physicists design elaborate setups to test these predictions, pushing the limits of what can be observed and measured. This dynamic exchange between theory and experiment drives progress, with each iteration refining our understanding of the natural world. Take the example of underground particle detectors, which are engineering marvels in their own right. These facilities are designed to shield experiments from cosmic rays and other sources of background noise that could obscure the faint signals of proton decay. The effort involved in constructing and operating these detectors reflects the scale of the challenge. Proton decay is so rare, if it occurs at all, that detecting it requires monitoring enormous volumes of matter over many years. Yet despite the immense difficulty, researchers remain undeterred. The stakes are simply too high. Detecting proton decay would provide a direct glimpse into the workings of grand unified theories, potentially uniting our understanding of the fundamental forces of nature. It would also offer evidence that matter, the foundation of the physical universe, is not as stable as it seems, opening the door to entirely new questions about what lies beyond. Even if proton decay is never directly observed, the implications of the hypothesis itself have already shaped the way we think about the universe. The search for answers drives innovation in particle physics, astrophysics, and cosmology, fostering collaboration across disciplines and inspiring new generations of scientists. In this way, the proton decay hypothesis is as much about the process of discovery as it is about the answers we seek. Furthermore, the possibility of proton decay introduces a poetic element to the scientific narrative of the universe. It suggests that creation and destruction are two sides of the same coin, a continuous cycle of transformation that governs all things. Just as stars are born from collapsing clouds of gas and dust, only to end their lives in fiery explosions or quiet fade-outs, so too might matter itself have a beginning, middle, and end. Ultimately, the study of proton decay is a testament to the human spirit, our ability to ask profound questions, confront the unknown, and persist in the face of uncertainty. Whether or not protons decay, the search for answers reveals as much about us as it does about the universe. It shows our capacity for wonder, curiosity, and resilience, even when the answers we seek lie on timescales far beyond our own lifetimes. As we continue to probe the mysteries of proton decay, we are reminded of the interconnectedness of all things. The same protons that may one day decay are the ones that make up the atoms in our bodies, the stars in the sky, and the fabric of the universe itself. Their story is our story, a tale of transformation, impermanence, and the unending quest to understand the cosmos. As we push forward in our quest for understanding proton decay, the potential answers to these profound questions may not only shape our conception of the future of the universe, but also lead to entirely new fields of exploration. We're standing on the precipice of scientific discovery, where each new experimental finding has the potential to unravel deep mysteries about how everything in existence works, from the most minute particles to the grandest cosmic structures. But before this, it's essential to dive into the very nature of the forces that govern proton decay and their implications. At the heart of the proton decay hypothesis is the concept of symmetry and the unification of the forces of nature. This is where the theory of grand unified theories, GUTS, comes into play. According to Guts, at extremely high energies, such as those present just moments after the Big Bang, the fundamental forces of nature, gravitational, electromagnetic, weak nuclear, and strong nuclear, were once a single unified force. As the universe cooled, these forces separated into their current distinct forms, each governing different interactions at various scales. This unification implies that, in theory, under certain conditions, particles like protons could behave in ways that would be impossible under our current understanding of physics. For instance, the strong nuclear force, which holds protons together in the nucleus of an atom, is a force that operates at a subatomic level. Normally, protons are incredibly stable, largely because of the power of this force. However, under the extreme conditions described by Guts, the energy required to maintain this strong bond might eventually be too much for even protons to handle, causing them to decay. This decay could take place in a variety of forms, but it's the theory of such possibilities that opens the door to imagining a universe where nothing, no matter how seemingly solid, remains immune to the passage of time. For years, the focus has been on experiments trying to detect proton decay, even though the timescales required are so immense that observing it within a human lifespan seems nearly impossible. The fact that no such detection has been made yet doesn't invalidate the hypothesis but rather emphasizes how little we still know about the fundamental workings of the universe. Proving the existence of proton decay, or even observing its first signs, would be a discovery of unimaginable importance, perhaps one of the most groundbreaking moments in modern physics. Interestingly, the search for proton decay has spurred some of the most innovative technologies in particle physics. The detectors used to hunt for proton decay are so sensitive and so finely tuned that they have applications beyond their original design. For example, Supercameo Candy, one of the largest and most advanced detectors, serves not only to observe proton decay but also plays a crucial role in the study of neutrinos. The knowledge gained from designing and operating these detectors has led to advancements in many areas of physics, creating opportunities for breakthroughs that extend far beyond the study of just one particle. What's perhaps even more fascinating is that proton decay, while still theoretical, holds the potential to reshape our entire understanding of the cosmos. If protons do decay, the implications would not be confined to theoretical physics or the study of subatomic particles. They would fundamentally alter our view of matter, energy, and time itself. If the building blocks of matter are not as permanent as we once believed, what does that mean for our understanding of the universe's past, present, and future? In particular, proton decay challenges our understanding of cosmological timelines. If protons have a finite lifespan, the concept of an eternally stable universe, one where matter is conserved forever, becomes obsolete. Instead, the universe would be gradually disassembling itself, albeit at a glacial pace. Galaxies would slowly fade as their protons break apart. The stellar objects we see in the night sky today, stars, planets, and galaxies, would eventually dissolve into their most basic, fundamental constituents. At some point, even the remnants of black holes might evaporate due to a process known as Hawking radiation, adding yet another layer of complexity to this ultimate cosmic transformation. This vision of a universe gradually fading into emptiness over unimaginable timescales might sound bleak, but it also underscores something profoundly beautiful: the transience of existence. The realization that everything, no matter how enduring it seems, is subject to change, decay, and eventual dissolution highlights the preciousness of life and existence in the here and now. While humanity may never witness the end of matter itself, the search for proton decay connects us with a larger cosmic narrative, one that transcends human history and reminds us of the vastness of the universe. In some ways, this concept of decay touches on our personal experience of time. Every living being is caught in the flow of time, subject to the forces of change and entropy. While our lifespans are far shorter than the potential lifespan of a proton, we, too, are part of this grand cosmic process. The awareness of our mortality and the impermanence of the things around us is something that philosophers and thinkers have grappled with for centuries. The possibility of proton decay pushes these reflections to a cosmic scale, forcing us to think about our place in the universe on a level far grander than we might have imagined. On a more practical level, the study of proton decay also influences how we think about the future of science and technology. If proton decay is eventually observed, it would open up new avenues of inquiry into the fundamental forces of nature. Researchers would undoubtedly be eager to explore how proton decay fits into the broader framework of quantum mechanics and relativity. This, in turn, could lead to advances in technologies we can't yet even conceive of, pushing the boundaries of what's possible and propelling humanity further into the realm of the unknown. One of the most intriguing aspects of proton decay is that it bridges the very small and the very large. At the particle level, we're dealing with forces that govern the behavior of quarks and leptons, the fundamental building blocks of matter. But proton decay also speaks to the evolution of galaxies, the ultimate fate of stars, and the end of the universe. In this sense, the study of proton decay isn't just about the small, subatomic world, it's also about the larger cosmic structure that surrounds us and the eventual fate of everything in it. As we continue to refine our models and improve our technology, the proton decay hypothesis may eventually offer answers to some of the most profound questions in cosmology. It's a reminder that the universe is not a static, unchanging place but rather a dynamic system in constant flux. No matter how stable or eternal something may seem, change is inevitable, whether that change happens over a few seconds or over billions of years. The search for proton decay is ultimately more than just a scientific quest. It's a journey into the very heart of the universe itself, a reminder that even the smallest building blocks of matter are part of a much larger cosmic story. And as we continue to explore the frontiers of physics, the mystery of proton decay will undoubtedly remain a central piece of the puzzle, offering new insights into the nature of reality and our place in this ever-changing universe. The search for proton decay leads us into deeper waters, extending far beyond the realm of theoretical physics and into questions about the future of the universe. If the protons that make up everything we know are indeed transient, it would mean that everything that exists, including us, might eventually return to a state of non-existence, not in some sudden burst of destruction, but through the slow, inevitable disintegration of matter. This idea challenges everything we understand about stability, time, and even the very nature of the universe itself. How could something as fundamental as the proton possibly decay? And what does that say about the ultimate fate of the universe? To begin addressing these questions, we need to explore the mathematical models and theoretical frameworks that support the idea of proton decay. These models are built upon some of the most advanced theories in physics, such as quantum mechanics and particle physics. At the heart of these ideas is the assumption that the strong nuclear force, which currently binds protons and neutrons together, might not be as absolute as we think. In fact, it might decay over time, leading to the eventual dissolution of protons into other particles, such as positrons and neutral pions. This leads us to a critical issue. The timescales involved in proton decay are staggeringly long. Current estimates suggest that the half-life of a proton, if it is even capable of decaying at all, could be on the order of 10 to the power of 34 years, which is far beyond the age of the universe itself. To put this into perspective, the universe is roughly 13.8 billion years old, which is less than 10 to the power of 10 years. So, even if proton decay is real, we would not expect to observe it anytime soon. This introduces a paradoxical challenge for scientists. How can something that takes so long to occur be experimentally verified in any meaningful way? Despite these challenges, there are several ongoing experiments designed to detect proton decay. For instance, the aforementioned Super Kamiokande detector in Japan is one of the most sensitive devices ever created to study proton decay. This massive underground experiment monitors over 50,000 tons of water to look for the rare interactions that could indicate a proton has decayed. The detector is capable of identifying the fleeting flashes of light produced when high-energy particles, like neutrinos or protons, interact with the water. However, no proton decay events have yet been detected, which only raises the level of intrigue surrounding this phenomenon. While the technology to observe proton decay may be in its infancy, researchers continue to refine their techniques and models to get closer to verifying this elusive concept. The search for proton decay represents one of the most ambitious scientific undertakings in history, and the implications of its discovery would resonate far beyond particle physics. For one, it would validate grand unified theories, GUTS, which suggest that all the fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were once united in the early moments of the Big Bang. The potential confirmation of proton decay would also push the boundaries of our understanding of space and time. If protons do decay, it would offer an explanation for why the universe, as we observe it, is in a state of constant change and evolution. If all matter is in a state of decay, it would suggest that the very fabric of reality is dynamic, subject to forces that can't be fully predicted, no matter how advanced our technology becomes. The potential of proton decay to affect the structure of the universe doesn't just affect the tiniest particles. In fact, one of the most intriguing implications of this theory is the way it could reshape our understanding of galaxies and stars. While current scientific models show that stars are powered by nuclear fusion, this process is not eternal. Eventually, even stars will burn out and lose their energy, leading to the death of galaxies and the slow fading of the universe into darkness. If protons eventually decay, even the most stable structures in the universe would eventually crumble. The very building blocks of matter would dissolve, leading to a slow, cold death for the cosmos. This raises a fascinating concept in cosmology, the so-called heat death of the universe. The heat death scenario suggests that, over an unimaginably long timescale, the universe will reach a state of maximum entropy, where all energy is evenly distributed and no thermodynamic processes can occur. This is often portrayed as a lifeless, dark, and empty universe. The idea of proton decay fits neatly into this narrative, adding another layer of complexity to the ultimate fate of all things. However, the idea of the heat death scenario, while widely accepted, is still just one theory among many regarding the end of the universe. Other hypotheses, such as the Big Rip or the Big Crunch, offer different perspectives on how the universe might end. The discovery of proton decay could potentially provide new insights into these competing theories, or it might lead to the development of entirely new ideas about the future of the cosmos. Could the slow decay of matter eventually lead to a rebirth of the universe, or would it simply fade into nothingness? In the meantime, scientists are not only looking for proton decay in isolation but also considering the broader implications of this potential discovery. For example, if protons can decay, could other particles, like neutrons or even electrons, undergo similar transformations over time? What about dark matter or dark energy, the mysterious substances that make up most of the universe's mass and energy? Understanding the decay of protons might help unlock the mysteries of these elusive entities, which have long puzzled physicists and astronomers alike. Furthermore, exploring proton decay could ultimately offer insights into the nature of quantum gravity, a field that has long remained elusive to researchers. Quantum gravity seeks to unite the theory of quantum mechanics, which governs the behavior of the smallest particles, with general relativity, which describes the behavior of massive objects like planets and black holes. Currently, these two theories are incompatible, but the study of proton decay may provide clues that bridge the gap between them, offering a unified theory of everything that could revolutionize our understanding of the cosmos. The potential for proton decay to fundamentally change our view of the universe is immense, but it also underscores the idea that the universe is far more complex and unpredictable than we may have realized. Even as we uncover the mysteries of the subatomic world, new questions and challenges arise. The discovery of proton decay could be the key to unlocking the next frontier of physics, but it might also push us to rethink everything we thought we knew about the very fabric of reality. Proton decay represents not just a scientific curiosity, but a profound reminder of the transient nature of existence. It challenges us to consider our place in the universe and the fragility of everything we hold dear. Just as protons, the building blocks of matter, may one day decay, so too might all things eventually succumb to the forces of time and entropy. Yet, this idea does not necessarily diminish the beauty of life, the universe, and the search for knowledge. Instead, it highlights the importance of the journey itself, the exploration of the unknown, and the drive to understand the mysteries of existence, no matter how long it takes. The vastness of space presents an awe-inspiring backdrop to these questions. As we continue to explore the fate of the universe, we encounter a multitude of phenomena that challenge our understanding. Proton decay, as a potential endpoint for matter, forces us to think not only about the distant future but also about the intricacies of the universe's present state. For all the cosmic wonders we've uncovered, there's still so much we don't know, and proton decay is one of the most profound gaps in our knowledge. Let's consider the fundamental nature of protons themselves. These particles are an integral part of the atomic nucleus, along with neutrons. But protons are more than just subatomic building blocks. They are a manifestation of the strong nuclear force, which is the fundamental force that binds quarks together to form protons and neutrons. This is the force that holds the entire atomic nucleus together, preventing it from flying apart due to the repulsive electromagnetic force between the positively charged protons. At a deeper level, the strong nuclear force is mediated by particles called gluons, which act as the glue, holding quarks together. The interactions of these gluons and quarks are governed by a theory known as quantum chromodynamics, QCD. According to QCD, the strong force becomes more intense as quarks are pulled further apart, leading to a phenomenon known as asymptotic freedom. This essentially means that quarks are bound together so tightly that it takes an enormous amount of energy to separate them. However, under the right conditions, this force can become unstable, potentially leading to proton decay. This idea of instability, while counterintuitive, becomes more understandable when we realize that the laws of physics aren't as fixed as they might seem. In fact, they evolve. The nature of fundamental forces might change over time. The very concept of proton decay fits into this framework of evolution, suggesting that the forces holding matter together may not be as permanent as we think. This is where grand unified theories, GUTS, come in, which attempt to unify the three fundamental forces of particle physics: the strong nuclear force, the weak nuclear force, and electromagnetism. These theories, still in their infancy, suggest that at extremely high energies, these three forces might merge into a single, all-encompassing force. In some models, this unification process could eventually lead to the disintegration of protons. The exact mechanics of this process are still not entirely clear, but the fact that protons are not immune to the forces of time is a deeply unsettling idea. The notion that these fundamental particles could decay over timescales far exceeding the lifespan of our universe raises profound questions about the ultimate fate of everything in the cosmos. If proton decay becomes a recognized phenomenon, the implications would be seismic, both scientifically and philosophically. First, it would provide an elegant explanation for why the universe is not filled with an infinite amount of matter. Instead of lasting forever, matter might have a natural expiration date, which would explain the gradual expansion of the universe and the disappearance of structure. Stars burn out, galaxies disperse, and even the seemingly unbreakable protons would eventually decay, turning the universe into a vast, empty void of elementary particles. For those who work in cosmology, the prospect of proton decay offers a glimpse into the far-flung future of the universe. But it also opens up a number of intriguing questions that extend into realms we have barely begun to understand. For example, could proton decay help explain dark matter or dark energy? These mysterious substances, which make up most of the mass and energy in the universe, are known to interact with normal matter only through gravity, making them incredibly difficult to detect. If protons decay, the resulting particles might interact with dark matter in ways that could provide vital clues about its nature. Moreover, the search for proton decay challenges us to rethink the nature of time itself. Time, as we understand it, is often treated as an unchanging constant, an ever-present feature of the universe that flows forward at a steady pace. But when we consider proton decay, we are confronted with the possibility that even the most stable of things can change with time, albeit over incomprehensibly long periods. This disrupts our conventional understanding of time as a rigid framework and invites us to imagine a future where everything we know, even the fundamental particles of matter, will eventually disappear. What does this say about the nature of existence? Are we just part of an ongoing cycle, where everything must eventually fade, only to be reborn again? Or is the universe truly on a one-way path toward oblivion? For now, all we can do is speculate. The search for proton decay remains one of the most fascinating and perplexing endeavors in modern physics. Yet, even if we never observe proton decay in our lifetime, the mere fact that we are asking these questions is a testament to the boundless curiosity and determination of the human spirit. We are driven by a need to understand our place in the cosmos, to reach beyond the limits of our current knowledge, and to probe the deepest mysteries of the universe, no matter how unlikely or distant they may seem. In the coming years, scientists may develop new techniques, technologies, or theoretical frameworks that will bring us closer to answering the question of proton decay. Perhaps one day, we will discover that the universe is not just a place of constant change but a place of inevitable decay, where even the most stable of entities, like protons, are not immune to the ravages of time. And as we look further into the future of the universe, we might come to realize that proton decay is not just an abstract concept but a profound piece of the cosmic puzzle that tells us how everything, galaxies, stars, planets, and even life itself, will eventually cease to exist. For now, the mystery of proton decay serves as a powerful reminder that the universe is far more complex and transient than we may have ever imagined. It challenges our understanding of matter, time, and existence, and forces us to confront the possibility that the universe itself, like the protons within it, may not be as eternal as we once thought. The idea of proton decay is a harbinger of the ultimate fate of all things, a subtle and unnerving truth that resonates through every atom and galaxy, offering us a glimpse into a future that, though unimaginable, is an inescapable part of the cosmic cycle. The idea of proton decay invokes a sense of cosmic melancholy, as it forces us to acknowledge that even the most stable entities in the universe have an expiration date. The notion that protons, which make up the very building blocks of matter, could eventually decay and disappear entirely challenges our perception of permanence. It suggests that even the seemingly unchanging universe is subject to the ravages of time, and that the fabric of reality itself could eventually unravel. Yet, the search for proton decay is not just about pondering the end of matter, but also about pushing the boundaries of our knowledge. As we delve deeper into the theoretical frameworks that underpin this concept, we begin to explore the profound implications for our understanding of the fundamental forces of nature. In particular, the idea of proton decay is intrinsically linked to the unification of the forces, the possibility that the forces that govern the behavior of particles, such as the strong nuclear force, the weak nuclear force, and electromagnetism, could be unified into a single, all-encompassing force. The pursuit of this unified theory, known as a grand unified theory, GUT, has been a driving force in particle physics for decades. GUTs propose that at extremely high energies, these three forces might merge into a single force, which could explain many of the fundamental mysteries of the universe. This unification, however, is not without its challenges. It requires a deeper understanding of the nature of the universe and the interactions between particles, and it raises questions about the very fabric of reality itself. The potential link between GUTs and proton decay is an exciting avenue of research, as it suggests that the decay of protons could be a natural consequence of the unification of the forces. In certain GUT models, the strong nuclear force, which is responsible for holding protons and neutrons together in atomic nuclei, could gradually weaken over time. As a result, protons might eventually become unstable and decay into other particles, leading to the eventual breakdown of matter as we know it. This process, however, would take an incredibly long time. The timescales involved are so vast that they exceed the current age of the universe by many orders of magnitude. Proton decay, if it were to occur, might take billions or even trillions of years to become detectable. This is one of the reasons why proton decay has remained elusive. Scientists have yet to observe any definitive evidence of its occurrence. Nevertheless, the search for proton decay continues, with experiments designed to detect the faintest traces of this process being conducted in some of the most advanced laboratories on Earth. One of the key experiments in this search is the Superkamiokande detector, located deep underground in Japan. This massive facility is designed to detect neutrinos, elusive particles that are produced in processes such as nuclear reactions in stars. However, The Super Cameo Candy detector is also capable of detecting rare events, such as proton decay. Over the years, this experiment has been collecting data in the hopes of observing the first signs of proton decay. While no such event has been observed yet, the search continues, with scientists refining their techniques and expanding their understanding of the conditions under which proton decay might occur. The fact that proton decay has not yet been observed does not mean that it is impossible. In fact, many physicists believe that proton decay is a fundamental feature of the universe, albeit one that operates on timescales far beyond our comprehension. The reason it has not been observed yet may simply be because the current technology is not sensitive enough to detect such rare events. As technology continues to advance, we may one day be able to observe proton decay directly, shedding light on one of the most profound mysteries of the universe. But even if proton decay is never observed, its theoretical implications continue to shape our understanding of the universe. The idea that protons could eventually decay forces us to reconsider the fate of the universe itself. If protons are not eternal, what does that mean for the long-term future of matter? Will all matter eventually break down, leaving behind only a dark, empty universe devoid of structure? Or is there a way in which the universe will regenerate, giving rise to new forms of matter and new structures? Some theories suggest that the decay of protons could play a role in the eventual fate of the universe. According to the Big Rip theory, the universe is expanding at an accelerating rate, and if this acceleration continues, it could eventually tear apart all matter, including protons. In this scenario, proton decay would be just one part of a larger process of cosmic disintegration. The universe would expand until galaxies, stars, and even atoms themselves are ripped apart, leaving nothing but a scattered collection of elementary particles. Other theories, such as the Big Freeze or heat death, suggest that the universe will continue to expand and cool, eventually reaching a state of maximum entropy where no more useful energy remains. In this scenario, proton decay would contribute to the gradual breakdown of matter, with everything ultimately becoming a featureless, empty void. Regardless of which scenario ultimately plays out, the idea of proton decay forces us to confront the idea that the universe, like all things, has a finite lifespan. The search for proton decay is not just about understanding the fate of matter, but also about exploring the fundamental laws of nature. By studying the forces that govern the behavior of particles, scientists hope to uncover deeper insights into the nature of the universe itself. The possibility of proton decay raises profound questions about the nature of time, the evolution of the universe, and the ultimate destiny of all things. It challenges our understanding of the universe and forces us to reconsider the limits of our knowledge. As we continue to search for answers to these questions, we are reminded that the universe is not static, it is in a constant state of flux. From the birth of stars to the formation of galaxies, the cosmos is constantly changing and evolving. Proton decay, if it is real, would be just one part of this ongoing process of transformation. It would mark the end of one era of the universe and the beginning of another. In the grand scheme of things, proton decay is a tiny piece of the cosmic puzzle. But its implications are profound, as it touches on the very nature of matter, time, and the universe itself. The search for proton decay is not just about finding an answer to a scientific question, it is about understanding the deep, underlying forces that shape the cosmos and everything within it. As we look to the future, we can only speculate about what discoveries await us. Will proton decay be observed in the coming years, or will it remain an elusive mystery? Only time will tell. But in the meantime, the idea of proton decay serves as a powerful reminder of the fragility of the universe and the inexorable march of time. It is a testament to the ongoing quest for knowledge, and a reminder that the universe is far more complex and mysterious than we can even imagine. The journey into the possibility of proton decay does not just challenge our understanding of the universe at its most fundamental level, it also pushes the limits of our scientific imagination. It forces us to question the very nature of existence. What happens to matter when it ceases to be? What happens when protons, the essential particles that make up the nuclei of atoms, break down into their constituent components, and ultimately disappear? What are the consequences of such an event for the universe? And how does it affect the complex structures that we observe, from galaxies to individual cells? To fully comprehend the significance of proton decay, it's important to delve deeper into what protons are and why they are so critical to the fabric of the universe. Protons are subatomic particles, composed of quarks and gluons, which are bound together by the strong nuclear force. This force, one of the four fundamental forces of nature, is incredibly strong, but it operates over a very short range, keeping the quarks inside a proton tightly bound together. Protons are stable under normal conditions, and they make up the nuclei of atoms, which in turn make up the matter that forms everything we see around us. Without protons, there would be no atoms, no matter, and ultimately, no universe as we know it. The decay of protons is a theoretical possibility, one that arises from certain models in particle physics, particularly within the context of grand unified theories, GUTS, and beyond the standard model of particle physics. These theories suggest that at extremely high energies, the strong nuclear force, which holds protons together, could become weakened or behave differently, causing protons to break apart into lighter particles, such as positrons and neutral pions. This process would represent the slow but eventual breakdown of matter itself. If protons were to decay, it would not happen quickly. As we discussed earlier, current estimates suggest that the half-life of a proton is on the order of at least 10 to the power of 34 years, a time span far exceeding the current age of the universe, about 13.8 billion years. This means that proton decay, if it is real, would not be observable on human timescales. The decay would be an exceedingly rare event, making it extremely difficult to detect. This raises an important question: how would we ever know if protons are decaying at all? And if they are, what might that mean for the future of the universe? Detecting proton decay is a formidable challenge, but it is one that scientists are actively pursuing. As mentioned before, experiments like the Super Kamiokande detector, located in Japan, are specifically designed to search for signs of proton decay. The detector works by observing vast amounts of water, monitoring for any unusual events that could indicate the transformation of a proton into other particles. The detector's massive size and its location deep underground help shield it from interference from cosmic rays and other background noise, making it one of the best tools available for observing such rare phenomena. However, detecting proton decay is not just about the sheer scale of the experiment. It also requires a deep understanding of particle physics and a precise theoretical framework. The concept of proton decay is intimately tied to the unification of the fundamental forces, which is still one of the greatest unsolved problems in physics. In the standard model of particle physics, the strong nuclear force, weak nuclear force, and electromagnetic force are all distinct, but the idea of guts suggests that they could have been unified into a single force during the earliest moments of the universe, shortly after the Big Bang. If such unification occurred, it could explain why protons are stable today and why they might eventually decay. Some theories predict that proton decay could be linked to the much larger forces of nature, particularly those that govern the very fabric of space-time. These forces, such as gravity, could eventually come to play a role in determining the ultimate fate of matter. For instance, some speculative ideas suggest that in the distant future, as the universe continues to expand and cool, even the strongest forces may start to weaken. If this happens, the fundamental particles that make up matter could no longer hold together, and even the protons might decay into more basic components. In this view, proton decay is not just an isolated phenomenon, it's a natural consequence of the ongoing evolution of the universe. The study of proton decay is also intimately linked to the concept of entropy, the measure of disorder in a system. In thermodynamics, entropy tends to increase over time, driving systems toward a state of maximum disorder. The eventual decay of protons could be seen as part of this trend, where, over unimaginable timescales, even the most stable forms of matter succumb to the inexorable pull of entropy. In this scenario, proton decay could be the ultimate end state of matter, a final dissolution into the nothingness that awaits all things as time progresses. One of the more fascinating aspects of proton decay is that it raises questions not only about the eventual end of matter, but also about the fundamental constants of nature. If protons do decay, it could suggest that the basic laws that govern the universe are not as fixed and immutable as we once thought. The constants of nature, such as the gravitational constant and the fine structure constant, which determine the strength of the forces in the universe, could also change over time. This would have profound implications for everything we know about physics, from the formation of stars to the behavior of subatomic particles. Interestingly, the decay of protons could even have implications for our understanding of dark matter and dark energy, two mysterious substances that make up most of the universe's mass and energy but remain largely invisible to our current instruments. Some theories suggest that the decay of protons could be linked to the eventual transformation of normal matter into dark matter or dark energy, altering the very nature of the universe in ways that we can only begin to imagine. If proton decay is indeed part of the long-term future of the universe, it would mark the end of an era in the life of the cosmos. But would this be the ultimate end of everything? Perhaps not. Some theories posit that, even after protons decay, the universe might continue to evolve in ways that are beyond our current comprehension. It's possible that new forms of matter and energy could emerge in the distant future, as the laws of physics continue to evolve and give rise to new possibilities. One such theory is the idea of a recycled universe, where the end of one cosmic era leads to the birth of a new one. In this view, the universe could undergo a series of cycles, each one marked by the decay of matter and the rebirth of new forms of existence. The idea of a cyclical universe is supported by some interpretations of quantum mechanics and string theory, which suggests that the universe might not be a one-time event, but part of an infinite series of cosmic rebirths. The decay of protons also raises philosophical and existential questions. What does it mean for the universe to come to an end in such a slow and gradual way? What does it mean for our place in the cosmos if even the matter that makes up our bodies and the stars we see in the sky is destined to decay into nothing? These questions remind us of the fragility of existence and our limited understanding of the universe, and they challenge us to rethink our place in the grand, unfolding story of the cosmos. In many ways, the search for proton decay is a search for meaning, not just in the context of physics, but in the broader, cosmic sense. It challenges us to reflect on the transient nature of all things and to confront the inevitable conclusion that everything, every star, every planet, every particle, will one day cease to be. It forces us to consider the possibility that the universe we know and love may not be eternal, and that the very fabric of reality could unravel in the far-flung future. Ultimately, the mystery of proton decay is a reminder that the universe is an ever-changing, dynamic entity, and that our understanding of it is constantly evolving. The quest for answers to the questions raised by proton decay will continue to shape the future of science and our understanding of the cosmos. It is a journey that will take us into the deepest realms of theoretical physics, where we will continue to grapple with questions about the nature of time, space, and the fundamental forces that govern all existence. While proton decay may seem like an abstract and distant concept, it serves as a powerful symbol of the larger mysteries that lie ahead. It is a reminder that the universe is far more complex and mysterious than we can fully grasp, and that there is still much to learn about the nature of reality itself. As we continue to explore the idea of proton decay, the implications of such a phenomenon stretch far beyond the confines of particle physics. In fact, the concept invites us to reconsider our entire perspective on the universe, pushing the boundaries of our imagination and challenging the very framework within which we understand existence. Proton decay is not simply a theoretical curiosity. It forces us to confront the inevitable, though incredibly distant, fate of all matter in the cosmos. The idea that protons could decay over an unfathomably long period of time introduces an intriguing paradox. On the one hand, protons are some of the most stable particles in nature, and their longevity is one of the cornerstones of the standard model of particle physics. They are the building blocks of atomic nuclei, and they exist in vast numbers throughout the universe. The idea that protons might eventually decay seems almost absurd when placed alongside the concept of their enduring stability. It's a contradiction that creates a deep tension between our current understanding of the universe and the unsettling idea that nothing, absolutely nothing, can last forever. Proton decay also introduces the notion that, even in the far future, the universe will not simply run out of matter. Instead, it suggests a gradual and inevitable dissolution of all matter into its most fundamental components. While this might sound like the end of the universe, it doesn't necessarily mean the end of everything. Theories like the multiverse hypothesis or the idea of a cyclic universe suggest that the end of matter in one iteration of the cosmos might lead to the birth of a new universe with its own unique properties. This kind of thinking challenges our notion of finality and opens up a realm of possibilities where the universe's ultimate fate is not a singular event, but part of an ongoing cycle. In some of these theories, the proton decay could be part of a larger cosmic process, one that is connected to the ongoing evolution of the universe itself. This is not just the decay of particles, but the eventual breaking down of the very structures that we take for granted, from stars and planets to galaxies and clusters. The theory posits that, in the far distant future, the matter we know today may no longer have the same properties that make it recognizable to us. Protons and neutrons may cease to exist in their current form, and the universe could shift toward new, unknown states of matter, governed by entirely different laws. Whether this future state will be a chaotic, formless void, or whether it will give rise to a new type of reality, is a question that remains tantalizingly out of reach. This cosmic transformation is a slow process, so slow that it's almost unfathomable to us as human beings. But in the context of the universe's long-term future, proton decay represents the final frontier of understanding. It challenges us to explore the deepest reaches of science and to ask fundamental questions about the ultimate destiny of all things. It may even point to new, unimagined realms of physics and mathematics that we have yet to explore. As we approach the question of what proton decay means for our universe, it's essential to recognize that this event would not be instantaneous. The breakdown of protons into lighter particles is a statistical event, one that could occur at vastly different rates depending on the specific conditions of the universe at any given moment. Some protons may decay long before others, while some may never decay at all. This means that the process is, in a sense, random, even though the overall trend suggests that all protons will eventually decay given enough time. The randomness of proton decay also hints at deeper underlying mysteries within quantum mechanics. The behavior of protons and other particles at the quantum level is governed by probabilities rather than certainties. This probabilistic nature of quantum particles is a fundamental aspect of quantum physics that has perplexed scientists for over a century. The idea that proton decay could follow a probabilistic path adds another layer of complexity to our understanding of the universe's fate, suggesting that the ultimate end of matter might be governed by forces and processes that we are only beginning to understand. The potential of proton decay also brings us face to face with the idea of time itself. What does it mean to witness or understand a process that takes longer than the age of the universe? How do we, as finite beings, reconcile the fact that the universe itself may be on a trajectory that we will never fully experience? The decay of protons is a reminder that the universe operates on timescales far beyond human comprehension. It challenges us to rethink the nature of time, not as a linear, unidirectional force but as something that may have more complex, cyclic, or even nonlinear qualities that we are not yet equipped to grasp. Proton decay also forces us to consider the ultimate fate of life, as we know it, in the universe. While the idea of proton decay may seem to belong to a distant future, it is nonetheless a concept that makes us reflect on our place in the cosmos. In the grand scheme of things, our lives are a brief moment in the history of the universe. Our sun will burn out long before the protons in our bodies decay, but even then, the decay of protons may mark the final stage of the universe's transformation. As humanity continues to explore the vastness of space and understand the smallest particles of matter, the possibility of proton decay underscores the fragility of our existence. It reminds us that, while we have achieved extraordinary feats in understanding the universe, there are still forces at play that are far beyond our ability to control or predict. Proton decay serves as a humbling reminder of the ultimate impermanence of everything, including the very building blocks that make up the universe we inhabit. Proton decay is more than just a theoretical curiosity. It is a concept that forces us to look beyond the present moment and consider the long-term future of everything in the universe. Whether or not proton decay is a reality, it challenges our understanding of the universe's fate, its ultimate end, and the limits of scientific inquiry. As we continue to probe deeper into the mysteries of space, proton decay stands as a beacon of the unknown, a reminder that even the most stable and fundamental components of the universe may, one day, dissolve into the nothingness of time. The exploration of proton decay not only challenges our current understanding of the universe but also opens doors to new theories that could redefine our fundamental grasp of space, time, and matter itself. As we try to peer into the distant future where protons may no longer exist, the consequences of such a transformation grow more profound. What does it mean for the physical structures of the universe, from the smallest particles to the largest galaxies? Can we even begin to imagine what a universe without protons might look like, and more importantly, what kind of physics would govern it? To understand the potential impact of proton decay, we must first examine the concept of matter itself. Matter, as we experience it today, is composed of atoms, and atoms, in turn, are made up of protons, neutrons, and electrons. Protons are the positively charged particles in an atom's nucleus, holding the nucleus together and determining the chemical properties of an element. Without protons, atoms could not exist in their current form, and with them gone, all structures, from simple molecules to complex living organisms, would cease to be. But what happens if protons slowly decay over time, eventually disappearing? The answer lies in the deeper understanding of what happens to the building blocks of our universe on extraordinarily long timescales. This process, although theoretical and still not fully understood, suggests a time when the universe might be left with nothing but a thin soup of elementary particles, where even the atoms that make up stars, planets, and life are no longer stable. In this context, proton decay seems less like a sudden cataclysm and more like a slow, creeping inevitability. The implications of this slow decay are difficult to fully grasp, particularly when we consider that proton decay might take as long as 10 to the power of 34 years, a time span vastly exceeding the current age of the universe, which is about 13.8 billion years. This means that even if proton decay is a reality, it would be an event far removed from our human experience. Yet this doesn't make it any less significant. The slow, drawn-out decay of protons would mark the final end of matter as we know it, and for all practical purposes, this would signal the conclusion of the current universe's existence. However, this end of matter might not necessarily be the end of the universe itself. Some cosmological theories propose that the universe could eventually undergo a big freeze, or a big rip. But proton decay adds a new, dramatic twist to these scenarios. Even as stars burn out and galaxies drift apart, the decay of protons could signal the slow destruction of the very fabric of reality. The once stable building blocks of the universe, from the smallest atoms to the largest cosmic structures, could disintegrate over unimaginable spans of time. In this far future, the universe might be a desolate, empty space, with only remnants of its former self, particles and radiation drifting in the cold void. While this scenario sounds bleak, it's important to remember that this process is still purely theoretical, and there are numerous factors that could influence the ultimate fate of matter. For instance, the detection of proton decay, while sought after through various experimental means, has not yet been conclusively observed. Scientists have been working for decades to measure proton decay, but their efforts have thus far come up empty. In fact, the very fact that proton decay has not been observed yet strengthens the argument that it may take an unimaginably long time, far beyond the lifespan of human civilization, to occur. Moreover, the search for proton decay is not just a matter of scientific curiosity. It could hold the key to understanding the most fundamental forces and particles that govern the universe. If proton decay were to be detected, it would provide evidence for new physical theories, including potential extensions of the standard model of particle physics. Proton decay could be the final piece of the puzzle that reveals the true nature of matter and energy, offering us insights into the early universe, the formation of galaxies, and the mechanisms that will shape its ultimate demise. Beyond the implications for particle physics, the concept of proton decay invites us to contemplate larger philosophical questions about the nature of existence itself. What does it mean for a universe to be alive and active one moment, and then gradually fade into an inert, lifeless state over billions of years. Can we reconcile the fleeting, transient nature of existence with our human desire for permanence and stability? Proton decay, in its most profound sense, forces us to confront the fragility of all things, reminding us that even the most fundamental particles we rely on for the very structure of reality could be subject to an eventual decay, returning everything to its primordial state. One of the most fascinating aspects of proton decay is its potential connection to the theory of quantum gravity. Quantum gravity, which seeks to reconcile quantum mechanics and general relativity, remains one of the most challenging and enigmatic areas of modern physics. Proton decay may provide a crucial window into understanding how these two fundamental forces interact on the smallest scales. If the proton does indeed decay, this would require a new framework of physics that could potentially unify all the forces of nature. The search for proton decay is therefore not only about studying the death of matter but also about opening new avenues for understanding the nature of space, time, and the fundamental laws that govern the universe. Additionally, proton decay is closely tied to some of the most groundbreaking and speculative areas of cosmology, such as the multiverse theory and the possibility of multiple universes. According to the multiverse hypothesis, our universe is just one of many that exist in a vast cosmic landscape. If proton decay does occur in our universe, it might signal a transition to a new phase, perhaps leading to the creation of an entirely new universe with different physical laws. In this sense, proton decay could be part of a cyclical process that governs the life and death of universes, suggesting that our universe might not be the first or the last to exist. The idea of a multiverse, where multiple universes undergo their own birth, evolution, and eventual decay, adds a layer of complexity to the already mind-boggling concept of proton decay. If the decay of protons marks the end of our universe, what happens next? Will our universe be reborn in some form, or will its remnants give birth to a new cosmic reality, with new laws of physics and new forms of matter? Theories such as eternal inflation and the idea of a Big Bounce propose that the universe could undergo an endless series of cycles, each one leading to a new phase of existence. In this grand cosmic tapestry, proton decay may be just one chapter in an infinite story of creation, destruction, and rebirth. This cyclical view of the universe challenges the traditional idea of a linear, one-time creation and destruction, offering a more dynamic and fluid perspective on the nature of existence. If proton decay is part of this cycle, it suggests that the universe is far from a static, unchanging entity. Instead, it is a living, breathing system, constantly evolving and transforming, with each stage of its existence bringing new opportunities for discovery, understanding, and ultimately, rebirth. The possibility of proton decay raises profound questions about the meaning of life and the purpose of our existence within the larger framework of the universe. If everything, including the protons that make up the matter in our bodies, will eventually decay and disappear, does this diminish the significance of life itself? Or does it highlight the fleeting, precious nature of our existence, urging us to cherish each moment and seek understanding before the inevitable end? In the face of this overwhelming uncertainty, humanity continues to push forward, driven by a desire to understand the universe on its deepest level. Proton decay, whether it occurs tomorrow or billions of years from now, serves as a reminder of the impermanence of all things, yet it also invites us to explore the unknown, to search for answers to the questions that have baffled us for centuries. It challenges us to look beyond the horizon of time and consider our place in the vast, ever-changing cosmos. As we venture further into the concept of proton decay, it becomes apparent that the scientific journey behind this hypothesis is not just about studying individual particles or forces in isolation. Instead, it requires us to re-examine our entire understanding of the universe, from the tiniest particles to the vastest structures in space. The decay of protons could offer insights into the ultimate fate of matter, space, and time, and perhaps even the existence of other universes. This exploration forces us to ask profound questions about our place in the cosmos, the fleeting nature of existence, and whether there is any real permanence in the universe at all. At its core, the idea of proton decay is rooted in the attempt to reconcile our understanding of the forces governing the universe. The standard model of particle physics, which has served as the bedrock of our understanding for decades, has successfully explained much of what we observe in nature. However, it is incomplete. The standard model does not account for gravity, and it offers no explanation for dark matter or dark energy, two mysterious phenomena that seem to make up most of the mass energy content of the universe. It is in this context that the search for proton decay becomes especially important. Physicists believe that proton decay could provide evidence of a theory that unifies all of the forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Such a theory, often referred to as a grand unified theory, GUT, would explain how these forces interact at the most fundamental level. Proton decay could be a key signature of this unification, suggesting that at extremely high energy scales, the forces we perceive as distinct might merge into a single force. If proton decay is proven to occur, it would provide a profound insight into the nature of matter, time, and the universe itself. The search for proton decay is not easy. Since proton decay is expected to happen extremely slowly, detecting it requires highly sensitive experiments and vast amounts of time. Scientists have been looking for evidence of proton decay for decades, but so far, no conclusive evidence has been found. Experiments such as Super Kamiokande in Japan and the Proton Decay Detector at the Large Hadron Collider have sought to observe proton decay by detecting the rare signals that would result from such an event. These experiments rely on observing vast quantities of matter, usually in large, isolated volumes, to increase the chances of detecting a single instance of proton decay. Despite the lack of direct evidence, the search continues because of the immense implications proton decay could have on our understanding of the universe. Even though it may seem like a long shot, the discovery of proton decay would be a revolutionary event in physics, providing the missing link between quantum mechanics and general relativity, and perhaps shedding light on the nature of dark matter and dark energy. It could be the final piece of the puzzle that unifies the seemingly disparate forces of the universe into a single, elegant framework. The potential detection of proton decay also forces us to think about the nature of time itself. If protons are indeed decaying over an unfathomably long period, it suggests that the universe is in a constant state of flux, even if that change is imperceptible to us in the short term. This would imply that time itself is not just a static backdrop against which events unfold, but a dynamic and evolving force that shapes the universe. If proton decay is real, the universe is gradually marching toward an eventual end, but this end is far from imminent. Instead, it occurs over an incredibly long timescale, which is both comforting and unsettling at the same time. The death of matter, as a result of proton decay, brings us to the idea of the ultimate fate of the universe. While many cosmologists predict that the universe will continue to expand indefinitely, eventually reaching a state of heat death in which all stars burn out and all matter is spread thin across an ever-growing cosmos, proton decay adds an additional layer of complexity to this scenario. Heat death, in this context, would not be a final, cataclysmic event but rather a slow process that stretches across eons. As protons decay and atoms break apart, the very fabric of matter would dissolve into an ever-thinner collection of elementary particles, unable to form any lasting structures. Eventually, even these particles would decay, leaving behind nothing but a dark, empty universe. This scenario, though it may seem distant and abstract, challenges our perception of the cosmos as a permanent, stable entity. If protons, the building blocks of matter, can decay over time, then what else is subject to decay in the universe? Is everything, from the smallest particle to the largest galaxy, doomed to break down eventually? These questions raise profound philosophical issues about the nature of existence. Is there any permanence in the universe, or are we simply witnessing a fleeting moment in an endless cycle of creation and destruction? The decay of protons also forces us to reconsider the idea of the eternal nature of the universe. While the idea of an eternal universe has been a cornerstone of many philosophical and scientific discussions, proton decay introduces the possibility that even the most fundamental structures of the cosmos are not immune to the ravages of time. If protons decay, it suggests that the universe, in its current form, is not eternal but rather a transient phase in a much larger, ever-changing process. Despite the grand scale of proton decay and the implications it carries, it is important to remember that our current understanding of this phenomenon is still in its infancy. Scientists are only beginning to explore the potential effects of proton decay on the structure of the universe. Much more research is needed before we can fully understand its impact. However, the search for proton decay is one of the most exciting frontiers in modern physics, offering the promise of groundbreaking discoveries that could reshape our entire understanding of the universe. Proton decay is not just a theoretical concept that could explain the eventual death of matter. It is a window into the deepest mysteries of the cosmos. The search for proton decay may hold the key to unlocking the ultimate nature of the universe, providing insights into the forces that govern it and the future of all matter. As we continue to explore this phenomenon, we are not just searching for the decay of protons, but for answers to the most fundamental questions about existence, time, and the very fabric of reality. Whether proton decay is real or not, it reminds us that the universe is constantly evolving, and that even the most seemingly stable elements of matter may one day fade away, leaving behind a new and unknown reality. As we continue to explore the implications of proton decay, we must also confront the fact that this process, though seemingly distant, has profound consequences for everything we know about the universe. The slow and gradual decay of protons raises the possibility that the very fabric of reality is not as stable as we might have once thought. It challenges the idea that the universe, in its current state, is eternal or that its basic constituents, protons, neutrons, electrons, are immutable. This revelation, even if it takes place on a timescale far beyond human comprehension, forces us to rethink our fundamental understanding of time, space, and matter. To fully appreciate the scope of proton decay, we must delve into some of the more intricate aspects of particle physics. The strong nuclear force that holds protons and neutrons together in the nucleus of atoms is one of the fundamental forces of nature. This force is incredibly powerful, binding protons together with such intensity that the energy required to break these bonds is immense. Yet, despite this powerful force, there is the possibility that over unimaginable stretches of time, even protons themselves could break down. This raises the question of whether other forces, such as gravity and electromagnetism, are also susceptible to this form of decay over time. What would it mean for the very forces that govern the universe to fade away? The process of proton decay, as hypothesized, involves a proton transforming into lighter particles, such as positrons and neutral pions, over an extended period of time. The specific mechanism by which this occurs is still unknown, but it could be related to the interactions of high-energy particles in space. Some theories suggest that proton decay could be tied to the concept of quantum tunneling, where particles move through energy barriers that would normally be insurmountable. In this case, the decay of protons might occur as a result of such quantum effects, which take place over incomprehensibly long timescales. The idea that particles could leak through barriers, eventually causing their decay, is a mind-boggling concept that forces us to rethink our understanding of the limitations of nature's laws. In order to detect proton decay, scientists have devised ingenious methods of observation. Experiments like Supercameo Candy, located deep underground in Japan, are designed to look for signs of proton decay by observing neutrinos and other particles that might be emitted during the decay process. Supercameo Candy is a massive detector surrounded by a vast array of water, providing an ultra-sensitive environment for detecting the rarest of events. Despite decades of searching, proton decay has yet to be conclusively observed, and some scientists speculate that the process occurs so infrequently that it might take millions or even billions of years before we are able to detect its signature. While the search for proton decay is ongoing, its implications are already profound. If proton decay were to be confirmed, it would offer a glimpse into the far future of the universe, one in which matter, as we know it, no longer exists in its present form. The implications of this for our understanding of the cosmos would be staggering. It would suggest that all matter, not just protons but even the most stable elements, is subject to eventual decay. This realization would challenge the very notion of permanence in the universe. How can something that we perceive as stable and unchanging ultimately be vulnerable to disintegration over time? And what does this tell us about the nature of existence itself? Another fascinating aspect of proton decay is its potential connection to the idea of an ever-expanding universe. According to current cosmological models, the universe is continuing to expand, and this expansion is accelerating due to the influence of dark energy. As the universe stretches, it becomes increasingly sparse, with galaxies moving further apart and matter becoming more diluted. If proton decay is a real phenomenon, it could provide a physical mechanism for the gradual dissolution of matter in an expanding universe. Over time, as more protons decay and the atomic structure of matter breaks down, the universe could eventually reach a point where it is no longer composed of recognizable particles, but rather a scattering of elementary particles and radiation. This scenario, often referred to as the Big Freeze, or heat death, of the universe, would mark the end of the cosmos as we know it. In this context, proton decay becomes a key player in the long-term evolution of the universe. While the exact timescale for proton decay is still uncertain, current estimates suggest that the process could take anywhere from 10 to the power of 34 to 10 to the power of 36 years, far longer than the current age of the universe. Even though this may seem like an impossibly long period of time, it serves as a stark reminder that the universe is not static. It is constantly changing and evolving, albeit on a timescale that is far beyond human lifetimes or even the existence of our solar system. This concept of the universe's eventual dissolution raises profound philosophical questions about the nature of existence. If all matter is subject to eventual decay, then does anything truly last forever? What does it mean for us, as conscious beings, to live in a universe that is destined to gradually fade away? These are questions that have intrigued philosophers, scientists, and thinkers for centuries. Some might argue that the knowledge of proton decay and the ultimate fate of the universe makes our lives seem insignificant. After all, if the universe will eventually reach a state of complete entropy, where no structure or matter remains, what meaning can we derive from our fleeting existence? Yet, others might find comfort in the idea that the universe, though finite, has a story that stretches across vast eons. Even though matter may eventually decay and fade into nothingness, the journey of the universe, its birth, its evolution, and its eventual transformation, remains an awe-inspiring testament to the vastness of time and the complexity of existence. The search for proton decay, then, is not just an attempt to understand the fate of matter, but a journey into the heart of the universe itself, asking us to confront the ultimate questions of time, space, and existence. Furthermore, the search for proton decay has broader implications for our understanding of the very nature of time. Time, as we experience it, is usually thought of as a linear progression from past to future. But if protons can decay over immense timescales, it suggests that time itself might not be as straightforward as it seems. Could the passage of time be more complex than we currently understand, with different regions of the universe experiencing time in different ways? Could the decay of protons be a reflection of a deeper, more mysterious aspect of time that we have yet to comprehend? The potential discovery of proton decay would also have implications for our understanding of the fundamental forces that shape the universe. If proton decay is tied to a grand unified theory, GUT, as some scientists believe, it could open the door to a new era of physics, one in which we are able to unify the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, coherent framework. Such a theory could explain not only proton decay but also the mysteries of dark matter, dark energy, and the true nature of the cosmos. In this sense, proton decay could serve as a stepping stone toward a deeper understanding of the universe, bridging the gap between the known and the unknown. As we look to the future, the search for proton decay represents more than just a quest for knowledge about the ultimate fate of matter. It is a quest to understand the very nature of the universe itself. Whether or not proton decay is ever conclusively observed, the questions it raises about time, matter, and existence will continue to drive scientific inquiry for generations to come. And in the end, the journey to understand proton decay may prove to be just as important as the discovery itself, as it forces us to confront the mysteries of the cosmos in ways that challenge our deepest assumptions about reality. As we dive deeper into the mysteries of proton decay, One of the most intriguing aspects is the potential connection it has with some of the most fundamental questions in physics. Proton decay doesn't just touch on the nature of matter, it also intertwines with our understanding of symmetries, conservation laws, and the grand structure of the universe itself. One concept that arises from this potential phenomenon is the violation of baryon number conservation. In particle physics, the baryon number is a conserved quantity, meaning that in typical interactions, the total number of baryons, particles like protons and neutrons, remains constant. This principle has held true in every particle interaction we have observed so far. However, if protons were indeed to decay, it would violate this conservation law, signaling a deeper level of symmetry breaking in the universe's underlying structure. This raises important questions about the laws that govern particle interactions and whether they might be different in extreme environments, or at very high energy scales. If proton decay occurs, it would open the door to new types of particle interactions that could dramatically alter our understanding of how particles interact on the most fundamental level. The question of proton decay also takes us back to some of the most elusive concepts in physics: quantum mechanics and general relativity. These two theories, which serve as the pillars of modern physics, are notoriously difficult to reconcile. Quantum mechanics governs the behavior of particles on the smallest scales, while general relativity describes the force of gravity and the structure of spacetime on larger scales. Yet, these two theories, despite their success in their respective domains, appear to be fundamentally incompatible when it comes to describing extreme conditions, such as those near black holes or the very beginning of the universe. Proton decay might play a role in bridging these two frameworks. It is possible that proton decay, if observed, could offer clues about how the universe behaved in its earliest moments. As the universe began with the Big Bang, it underwent a rapid expansion known as inflation, where particles were created and interactions took place at energy levels far beyond what we can currently replicate in particle accelerators. Some theories suggest that proton decay might be linked to the conditions of the early universe when fundamental forces were unified, and the laws of physics as we understand them were dramatically different. If proton decay is ultimately linked to this period of cosmic history, it could provide a crucial piece of the puzzle in understanding how the universe evolved from a hot, dense state to the complex cosmos we observe today. However, we must also recognize that proton decay, if it is truly a rare and slow process, could remain undetectable for an incredibly long time. Our best current models suggest that protons have an extraordinarily long lifetime, potentially exceeding 10 to the power of 34 years. In practical terms, this means that proton decay is unlikely to be observed in the near future. Even with highly sensitive detectors, such as the Super Kamiokande experiment, the time required to gather enough evidence to detect proton decay could stretch far beyond the lifespan of humanity, and possibly even the Earth itself. This raises a profound philosophical question: how do we ascribe meaning to a phenomenon that is so distant in time? Do the mysteries of the universe matter only when they are observable within a human lifetime, or does the pursuit of knowledge have intrinsic value, regardless of when or if it can be witnessed? This very issue is what makes the study of proton decay so compelling. Even if we never observe proton decay in our lifetimes, the theoretical implications of such an event challenge the way we think about the universe's fate. It is a reminder that the universe is not a static, unchanging entity but rather an ever-evolving system. Just as protons themselves are subject to the forces that govern their decay, so too is the universe destined to undergo significant transformations over unimaginable timescales. This idea might be disconcerting to some. After all, the prospect of matter eventually ceasing to exist as we know it can feel unsettling. But for others, it is a fascinating opportunity to think beyond the present moment and to glimpse the universe in its most distant future. One of the key areas in which proton decay could reveal new insights is in the search for a unified theory of physics. For centuries, scientists have attempted to reconcile the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These forces operate on vastly different scales, from the subatomic to the cosmic, and understanding how they are connected has been one of the ultimate goals of theoretical physics. The grand unified theory, GUT is one possible framework that attempts to bring these forces together under one umbrella, suggesting that at extremely high energy levels, these forces might have been unified into a single force. Proton decay, if proven to occur, could be the key that unlocks this theory. The decay of protons may be the result of a deeper, more fundamental force that governs the interactions of particles at the highest energy scales. The search for proton decay is also closely tied to the broader quest to understand dark matter and dark energy. These mysterious substances make up approximately 95% of the universe's mass energy content, yet we know very little about them. Dark matter interacts with regular matter through gravity but does not emit, absorb, or reflect light, making it virtually invisible. Dark energy, on the other hand, is responsible for the accelerated expansion of the universe. Both of these phenomena remain some of the most perplexing mysteries in cosmology. Some scientists have proposed that proton decay might be related to dark matter or dark energy in ways that are not yet understood. For example, the decay of protons could release particles that interact with dark matter, potentially shedding light on the nature of this elusive substance. Alternatively, proton decay might be influenced by the presence of dark energy, which permeates the fabric of space and accelerates the expansion of the universe. If proton decay is ultimately found to be linked to dark matter or dark energy, it could have profound implications for our understanding of the universe's composition and evolution. As we approach the end of this exploration into proton decay, it's important to acknowledge the limitations of our current knowledge. Despite the best efforts of scientists and the deployment of some of the most advanced particle detectors in the world, proton decay remains an elusive mystery. The timescales involved are so long that even the most sensitive experiments have yet to observe any definitive evidence of proton decay. This may lead some to question whether we will ever have the technological capability to detect such an event, or if it will remain an abstract concept relegated to the realm of theoretical physics. However, the significance of proton decay goes beyond the technical challenges of detection. The hypothesis of proton decay forces us to confront the ultimate fate of the universe, the fragility of matter, and the nature of time itself. It challenges our assumptions about the permanence of the physical world and encourages us to think on a cosmic scale, where change is not just inevitable, but also a fundamental part of the universe's ongoing story. Whether or not proton decay is ever observed, the exploration of this idea opens up new frontiers in our understanding of the cosmos and forces us to reckon with the deepest, most profound questions about existence. As we look to the future, the search for proton decay and the questions it raises will continue to inspire physicists, cosmologists, and philosophers alike. Even if proton decay is never observed within our lifetimes, the implications of this idea will echo through the ages, reminding us that the universe is not a static entity but a dynamic, evolving system. The very fabric of reality may one day unravel, but that knowledge, in itself, will serve as a testament to our ability to look beyond the surface and ask the most fundamental questions about the nature of existence. As we continue to explore the profound concept of proton decay, we must also consider how it might impact our understanding of the nature of space and time. We tend to think of space as an unchanging, ever-present backdrop against which the events of the universe unfold. Time, similarly, is often seen as a constant, flowing from the past to the future in an orderly fashion. However, proton decay could force us to reconsider these assumptions. In the context of particle physics and quantum mechanics, the idea that protons may eventually decay challenges the very notion of stability in the universe. It suggests that even the fundamental building blocks of matter, things we have always considered to be constant, are not immune to the passage of time. In a universe where the most stable objects might eventually succumb to decay, how do we reconcile this with our understanding of time and space? Are the concepts of time and space themselves subject to change in ways we do not yet understand? If proton decay occurs, it could imply that there is a deeper, more fundamental process at play in the universe, one that operates on scales far beyond our current capabilities of observation. This process might suggest that time and space themselves are not the eternal, unchanging concepts we have long assumed them to be. Instead, they could be subject to fluctuations and transformations at extremely high energy levels or over vast periods of time. If protons decay, what does this say about the fate of other particles? Could the fundamental constants of the universe, such as the speed of light, the force of gravity, or even the laws of thermodynamics, change over time? These questions point to a universe far more dynamic and mysterious than we can currently fathom. At the heart of the proton decay hypothesis lies the idea of a final state for the universe, one where even the most stable elements of matter ultimately cease to exist. This end of matter scenario is unsettling, yet it has profound implications for how we understand the long-term evolution of the cosmos. If proton decay is true, it could signify the slow, inevitable collapse of all matter in the universe, transforming the cosmos into a state devoid of particles, atoms, and even the structures that define the universe as we know it. This vision of the future is both humbling and awe-inspiring, forcing us to confront the transient nature of existence. While the direct consequences of proton decay on our everyday lives are negligible, after all, the timescales involved are far beyond anything we can experience. The implications for the cosmos are far-reaching. For instance, as protons decay, so too would the stars that rely on protons for their nuclear reactions. Over unimaginable timescales, even the brightest and most enduring stars would eventually fade away, their protons slowly disintegrating until nothing remained but a cold, dark universe. This is a stark contrast to the vibrant, energetic universe we experience today, and it provides a humbling reminder of the fleeting nature of all things. Moreover, the concept of proton decay also ties into our current understanding of the second law of thermodynamics. This law states that in an isolated system, entropy, essentially the measure of disorder or randomness, tends to increase over time. As matter breaks down and protons decay, it could be seen as a process of entropy increasing at the most fundamental level. Over vast timescales, the universe may move toward a state of maximum entropy, sometimes referred to as heat death, where all matter and energy are evenly distributed, and no more work can be done. Proton decay might be one of the key mechanisms driving this inevitable process. This potential end state of the universe raises intriguing philosophical questions. If the universe is slowly decaying toward a state of maximum entropy, is there any way to reverse this process or avoid this ultimate fate? Some have speculated that proton decay could be connected to the idea of a cyclical universe, where the decay of matter is followed by a new Big Bang, a process that repeats itself indefinitely. In this view, proton decay wouldn't mark the end of everything, but rather the end of one cycle and the beginning of another. However, this idea remains speculative and highly uncertain, as we currently lack the observational evidence to support such theories. Interestingly, proton decay also brings us closer to the concept of time as an evolving dimension rather than a constant. For much of human history, time has been thought of as a fixed quantity, ticking forward at the same rate regardless of the events unfolding in the universe. But in light of proton decay and its potential connection to cosmic evolution, we may need to rethink our understanding of time itself. Time could be more fluid than we realize, with the behavior of fundamental particles like protons and the forces acting on them shifting over vast periods. This opens up a host of fascinating possibilities for the future of the universe and our understanding of reality itself. As we continue to investigate proton decay and its implications, we are also confronted with the limits of our observational tools. The fact that proton decay occurs over such long timescales makes it incredibly difficult to study directly. Current particle detectors are designed to observe subatomic particles over short timescales, and the slow process of proton decay would take longer than the lifetime of human civilization, let alone the age of a single experiment. This poses a challenge for scientists hoping to detect proton decay, as it might be impossible to observe such an event within a human lifetime. However, this limitation also underscores the importance of theoretical physics, which allows us to explore concepts and phenomena that may never be directly observable. Even if proton decay is never detected in a laboratory, its theoretical implications will continue to shape our understanding of the universe. At the same time, the search for proton decay and other fundamental phenomena can be viewed as part of a broader effort to explore the unknown and push the boundaries of human knowledge. The mysteries of the universe, from the nature of dark matter and dark energy to the potential for proton decay, challenge us to think beyond the confines of our immediate surroundings and to consider the larger cosmic picture. These questions force us to confront the limits of our understanding and to accept that there is still much we do not know about the universe, even in the most basic aspects of matter itself. Proton decay represents a window into the distant future of the universe and a reminder that the universe is a dynamic, ever-changing entity. The implications of proton decay go far beyond the realm of particle physics. They reach into the very heart of cosmology, philosophy, and our understanding of the nature of existence. Whether or not we ever observe proton decay in our lifetimes, the mere contemplation of this phenomenon enriches our understanding of the universe and our place within it. The idea that protons may one day decay, signaling the eventual end of matter, is both a scientific puzzle and a profound cosmic thought experiment. It forces us to consider the universe on timescales far beyond what we experience, and challenges us to rethink our assumptions about the permanence of matter and the passage of time. While the timescales involved may be daunting and the process of decay incredibly slow, the potential for proton decay to provide insight into the ultimate fate of the universe is a powerful motivator for scientists and philosophers alike. The search for this elusive event continues, driven by the same curiosity and wonder that has propelled humanity's exploration of the cosmos for centuries. As we continue to explore the mysteries of proton decay, we are reminded that the universe is far from static. The matter that makes up our world, the stars, and even the very atoms in our bodies is not eternal. Instead, it is part of a dynamic, ever-evolving process that will one day reach its conclusion. Proton decay, whether we witness it in our lifetimes or not, offers a glimpse into the distant future of the universe and challenges us to think on the grandest scales imaginable. It is a reminder that, in the end, all things, matter, time, and space, are subject to change, and the universe's ultimate fate is still a mystery waiting to be uncovered. As we continue to explore proton decay, it's important to realize that this hypothesis not only challenges our understanding of time and matter, but it also brings us to the edge of some of the deepest philosophical questions about existence. The decay of protons would represent the slow death of all matter, a process that could eventually lead to a universe entirely devoid of structure and substance. However, even as we imagine this distant and dismal future, the sheer scale of time involved is one of the most remarkable aspects of this concept. The timescales are so vast that it's nearly impossible for human minds to truly grasp their enormity. It puts into perspective just how fleeting our own existence truly is compared to the cosmic timeline. What makes proton decay so fascinating is that it touches on some of the fundamental assumptions we've long held about the universe. For centuries, scientists have viewed the protons that make up the nuclei of atoms as stable, unchanging entities. In fact, the idea that protons might decay over time goes against what we observe in nature. Protons seem unchanging, providing the foundation of all atomic structure, from the simplest hydrogen atom to the most complex elements in the periodic table. But the proton decay hypothesis suggests that this apparent stability is merely an illusion, a temporary phase in the life of a universe that will eventually succumb to entropy. This idea raises a host of questions. If protons decay, what else in the universe might be subject to decay in a similar way? Could other elementary particles undergo transformations we don't yet understand? Might there be other forces at work in the universe that we have yet to detect or fully comprehend? These questions expand beyond the realm of protons and lead us to the larger issue of the nature of reality itself. Proton decay forces us to think about the very fabric of the universe, and whether the building blocks of matter are as stable as we once believed. However, as unsettling as the idea of proton decay may be, it has profound consequences for our understanding of cosmology. If protons, which are the most stable particles we know, eventually decay, what does this say about the eventual fate of the universe? How do we interpret the cosmos in light of this potential outcome? The slow disintegration of all matter, and by extension, all structures in the universe, leads to the idea of a final, cold, and dark universe. This is the so-called heat death, or Big Freeze, scenario, where the universe continues to expand, and all matter decays into an increasingly diluted, lifeless state. The heat death theory suggests that as matter decays and stars burn out, There will be no more sources of energy to sustain life or even the basic processes we observe today. The universe would become an expansive and dark void, with only faint traces of energy lingering in the form of black holes, dark matter, or radiation. There would be no more stars to light the sky, no more galaxies to behold, and no more protons to hold the matter together. In essence, proton decay is seen as the inevitable step toward this dead state of the universe. It's a final conclusion to the story of the universe, one that seems both tragic and inevitable. But what is truly fascinating is the way proton decay connects to other major scientific theories. Take, for instance, the concept of the multiverse. If proton decay happens, it could serve as a clue that our universe is not the only one that will eventually reach this heat death scenario. Some multiverse theories suggest that there may be many universes, each with its own set of physical laws and properties. In this context, proton decay might be a universal truth, not just for our own universe, but for all of existence. This idea aligns with the notion that the universe may be cyclical in nature, constantly transitioning from one phase to another, with new universes emerging and old ones decaying into nothingness. Another area of study that intersects with proton decay is quantum mechanics. The instability of protons over time is a problem that sits at the intersection of particle physics and quantum theory. Quantum mechanics is the field of science that governs the behavior of subatomic particles, such as electrons and quarks. It introduces the concept that particles do not have definite positions or speeds until they are observed. In the context of proton decay, quantum mechanics tells us that there is a certain probability that a proton could decay at any given moment, though the timescales involved are so long that the probability is effectively zero over any human lifespan. However, this notion of probabilistic events, where the future is never certain, but can only be described in terms of likelihood, adds a layer of uncertainty to our understanding of the universe. The connection between proton decay and quantum mechanics also brings us back to a core concept in physics: the nature of force and energy. If protons decay over time, it suggests that even the strongest forces in the universe, such as the strong nuclear force that holds protons together, may eventually be overcome or diminished. This challenges our assumptions about the permanence of natural laws and forces. Is it possible that over incredibly long timescales, the very laws of physics could shift or break down? Proton decay could be a signal that our understanding of these laws is incomplete, and that they may operate differently over vast stretches of time, or in different regions of the universe. The search for proton decay is also a journey of observation and discovery that underscores the limits of current technology. As mentioned earlier, the timescales involved in proton decay are so immense that we might never directly observe it happening in a laboratory setting. Proton decay is incredibly rare, and detecting such an event would require extremely sensitive equipment capable of measuring events on timescales far beyond what is possible today. Physicists are working on building detectors that might one day catch the faint traces of proton decay, but we are still in the early stages of this effort. One proposed method for detecting proton decay involves using massive detectors like the Superkamio Candy in Japan, which is a large underground neutrino observatory. This detector is designed to observe rare interactions between neutrinos and other particles. If proton decay is a real phenomenon, it might leave behind a faint signal detectable by these types of instruments. However, the odds of observing proton decay are so small that it could take many decades, if not longer, to get conclusive evidence. Still, the search for proton decay is important because it could provide new insights into some of the deepest mysteries of the universe. The potential discovery of proton decay could also have profound philosophical implications. If the building blocks of matter are not as eternal as we once thought, what does this say about the nature of existence? Does it mean that everything we see, experience, and hold dear is destined to fade into nothingness? The very fact that proton decay may eventually signal the end of all matter forces us to confront the ultimate question: what is the purpose of the universe, and what happens to existence once it has reached its final stages? At the heart of this mystery lies one of the most important concepts in physics: the conservation of energy. The idea that energy cannot be created or destroyed, only transformed, has long been a cornerstone of our understanding of the physical world. But if proton decay leads to the disintegration of all matter, it raises new questions about the ultimate fate of energy. Can energy continue to exist in some form even after all matter has decayed, or is it lost to the universe forever? If proton decay is part of the process of the universe's eventual entropy, does this mark the true end of everything? Or could it simply be a transitional phase in a much larger, cosmic cycle? All of these questions point to the importance of continuing to explore proton decay and its potential implications for the universe. Whether or not we ever observe proton decay in our lifetimes, the very idea of it challenges us to think on the grandest scales and reconsider the nature of reality itself. As science advances and our understanding of the universe deepens, we may one day discover answers to these questions, and in doing so, gain a deeper insight into the ultimate fate of the cosmos. Proton decay may seem like an esoteric and distant concept, but it touches on some of the most profound questions we can ask about the nature of the universe. The idea that protons, the building blocks of matter, may eventually decay is a challenge to our understanding of stability, time, and the laws of physics. It opens up a universe of possibilities, from the slow death of all matter to the implications for time and energy. Whether or not we ever observe proton decay directly, the search for it remains one of the most intriguing and vital areas of scientific inquiry. It forces us to think on timescales and dimensions far beyond our immediate perception and challenges us to reconsider the very nature of existence itself. The potential discovery of proton decay opens up a vast range of scientific, philosophical, and even metaphysical questions. For decades, proton decay was considered a theoretical curiosity, a hypothetical scenario so unlikely that it was essentially dismissed as a far-off possibility. Yet, as more advanced technologies emerge and as physicists delve deeper into the unknown realms of particle physics and cosmology, the idea of proton decay is moving from mere speculation to something that could one day be observable. And while the concept itself remains deeply fascinating, it forces us to confront our very understanding of time, the universe, and the future of everything we know. One of the most fascinating implications of proton decay, and the broader concept of the eventual decay of matter, is how it aligns with some of the greatest mysteries of cosmology. When we think of the fate of the universe, we often imagine a future defined by the collapse of stars, the final cooling of galaxies, and the ultimate death of everything we recognize as life. The concept of proton decay ties directly into these long-term scenarios. This might sound like the stuff of science fiction, but it's also deeply connected to real scientific theories about the heat death of the universe. The heat death theory suggests that, over the course of an unfathomable period of time, the universe will experience an unstoppable and irreversible decline. With stars burning out, matter decaying, and energy dispersing into the vastness of space, everything will eventually settle into a state of maximum entropy. This concept, originally proposed by the second law of thermodynamics, posits that everything in the universe moves toward a state of disorder. Entropy increases over time, and once the universe reaches this point, there will be no more usable energy. It will be cold, dark, and empty. The decay of protons fits perfectly into this bleak vision of the future. This heat-death scenario raises some difficult questions about the nature of existence. If the universe is destined for a state of lifelessness, where even the building blocks of matter break down into nothingness, what is the point of all that came before? Does the ultimate demise of all matter signal the end of meaning itself? The search for proton decay, along with our exploration of cosmic phenomena like black holes, dark energy, and the expansion of the universe, forces us to confront some of these existential questions head-on. It's almost as if, in studying proton decay, we're looking into the future of everything, including ourselves. But there's another side to this narrative. While the potential discovery of proton decay might paint a grim picture of the future, it also serves as a profound reminder of how much we don't yet understand. The universe is full of hidden mysteries, and while the decay of protons might signal the eventual end of matter as we know it, we are just beginning to scratch the surface of what could be possible in the distant future. What if the decay of protons is merely the beginning of a new chapter in the life of the universe? Could this process lead to the creation of something entirely new, something beyond our comprehension? There are some theories that suggest that the eventual decay of protons could lead to a new phase of cosmic evolution. Perhaps the disintegration of matter, over incomprehensible timescales, could lead to the creation of entirely new structures, governed by principles we have yet to discover. Some cosmologists and physicists speculate that the ultimate fate of the universe is not one of absolute destruction, but one of transformation, a transformation that could mark the beginning of a new kind of existence altogether. After all, if proton decay is happening in our universe, who's to say that other universes, if the multiverse theory holds true, won't experience different phenomena in their own timelines? The multiverse theory suggests that there could be an infinite number of parallel universes, each with its own unique set of physical laws and constants. Some of these universes may operate according to different principles altogether. If proton decay occurs in our universe, it might be happening in other universes as well, but the outcome could be radically different. Perhaps matter doesn't decay in the same way, or maybe other fundamental particles undergo transformations we can't even imagine yet. Proton decay could be part of a broader cosmic evolution that transcends the boundaries of our own universe, linking it with other realms of existence. There are also theories suggesting that proton decay could tie into the idea of quantum gravity, and the search for a unified theory of everything. Quantum gravity is the field of physics that attempts to combine the principles of quantum mechanics with general relativity. If scientists are able to successfully develop a theory of quantum gravity, it could revolutionize our understanding of proton decay and other cosmic phenomena. It's possible that a unified theory could explain how protons decay and why certain forces behave in the way they do, opening the door to new insights into the very nature of matter, time, and space. While proton decay presents a fascinating avenue for exploration, it is ultimately a deeply humbling concept. It reminds us of the limits of human understanding. We are constrained by the short span of time we experience, and even our most advanced instruments may not be able to detect proton decay for many years to come. The search for this elusive process forces us to grapple with the notion that our grasp of the universe is limited. But in this limitation lies the beauty of science. Every discovery, every new insight, brings us one step closer to understanding the fundamental nature of existence. As we continue to search for proton decay, we are also reminded of how far we have come in our understanding of the universe. From the earliest days of human inquiry, when the nature of matter was shrouded in mystery, to the modern era of high-energy physics and advanced particle accelerators, our journey has been one of immense discovery. Proton decay, if it is ever confirmed, would be one of the most profound discoveries in the history of science. It would fundamentally change our understanding of the universe and the very nature of existence itself. But even if proton decay remains an elusive mystery for many years to come, the search itself is valuable. It forces us to think in new ways, to question old assumptions, and to reimagine the future of the universe. In the end, it may be the search for answers, rather than the answers themselves, that proves to be the most significant achievement. And perhaps, in our pursuit of knowledge, we will discover that the true meaning of existence lies not in the answers we find, but in the questions we continue to ask. The mystery of proton decay also highlights the inherent limitations of the scientific process. Despite all our advancements, the search for the decay of the proton requires tools far beyond anything that even the most sophisticated particle accelerators can currently provide. To detect proton decay, scientists would need to observe an event that, by its very nature, happens at a nearly infinitesimal scale, over an incredibly long period of time. In a sense, proton decay may remain beyond the reach of current technology, forcing us to rely on theoretical frameworks and indirect evidence to support our understanding. This highlights a tension that exists within modern science. While our theories grow ever more complex and refined, the mysteries we face grow ever more elusive and enigmatic. In the quest for knowledge, proton decay challenges our assumptions about time itself. The timescales involved in observing proton decay are so long that they force us to reconsider the meaning of now. The life expectancy of protons is estimated to be around 10 to the power of 34 years, vastly exceeding the current age of the universe, approximately 13.8 billion years. By the time proton decay would actually become detectable, it's possible that humanity, if it still exists in some form, may no longer have the means to even observe the process. The decay of matter, then, becomes a reminder of the fleeting nature of existence. One could argue that the contemplation of proton decay is not just an intellectual pursuit, but a reflection of the human desire to make sense of our place in the cosmos. Our curiosity about the ultimate fate of matter, and indeed the universe itself, speaks to a deeper existential longing. What happens when the building blocks of reality break down? Are we seeing the universe in its final stages? Or is this merely another chapter in an infinite cosmic cycle? Some have even drawn philosophical parallels between the idea of proton decay and the human condition. Just as protons might decay over unimaginable timescales, so too do the structures we create and the societies we build. Nothing is immune to the ravages of time. In this sense, proton decay isn't just a distant, abstract concept but a symbol of our own impermanence. The universe, it seems, offers no guarantees. Just as the proton's integrity is ultimately compromised by forces we can't yet fully comprehend, so too are our civilizations and our lives subject to forces far beyond our control. Interestingly, proton decay challenges not only our understanding of the physical world but also our concept of information. In a universe where even the most fundamental particles eventually decay into nothingness, one might ask, where does the information stored within those particles go? If matter breaks down, does the information it contained vanish with it? Or does it, in some form, persist? This is a question that extends beyond the realm of physics and delves into the depths of information theory, a burgeoning field in which scientists are exploring the nature of information itself. If everything in the universe is ultimately reducible to information, does proton decay signify the loss of all information, or is there something more profound at play? These are the types of questions that come to mind when we contemplate proton decay. But the scientific community remains deeply divided over whether proton decay will ever be observed. While the theory is an exciting one, the experimental evidence is still lacking. In fact, some physicists believe that proton decay could be one of those rare phenomena that remains entirely hypothetical, impossible to prove or disprove within the confines of human observation. If proton decay doesn't occur in the way that scientists currently envision, will our models of particle physics need to be reworked again? Perhaps we are simply not looking at the universe from the right perspective. Yet, even without direct evidence, the theory of proton decay has profound implications for our understanding of cosmology. One of the most significant implications of proton decay is its potential connection to the concept of baryon asymmetry. This term refers to the imbalance between matter and antimatter in the universe. According to the standard model of particle physics, the Big Bang should have created equal amounts of matter and antimatter. However, for reasons that remain mysterious, matter vastly outnumbers antimatter. Some scientists believe that proton decay could be one of the key mechanisms responsible for this imbalance, as the decay of protons could gradually shift the universe from a state of symmetry to one where matter predominates. If proton decay is indeed real and observable, it would also have profound implications for the concept of time itself. In many ways, the process of proton decay offers a cosmic window into the distant future. Unlike other phenomena, proton decay might reveal the universe's ultimate destiny, a slow, inevitable decline. If we can measure this decay, it could provide insight into how long the universe can sustain itself before everything breaks down into entropy. Moreover, the search for proton decay is also a reminder of the vastness of the unknown. Despite all the knowledge we've accumulated over the centuries, there is still so much we don't understand about the nature of the universe. The very fact that something as fundamental as the proton, something we once thought was immutable, could eventually decay is a humbling realization. It serves as a reminder that our understanding of the universe is still in its infancy. Perhaps, as we push the boundaries of science, we will encounter even greater mysteries that we cannot yet imagine. The pursuit of knowledge is a journey, and the exploration of proton decay is a vital part of that journey. But whether or not we ever observe the decay of protons, or understand the deeper mysteries of matter itself, we can take solace in the fact that the pursuit of these questions is what drives us forward. Each answer, each discovery, only leads to more questions, and that, in itself, is the beauty of scientific inquiry. While proton decay might signal the eventual end of matter, it is also a reminder that the quest for knowledge is infinite. Even in the face of a universe that is slowly winding down, we continue to search, to wonder, and to explore. Proton decay, in all its mystery, embodies the very spirit of human curiosity, the drive to understand the unknown and to push the boundaries of what we know. Whether or not we will ever witness the ultimate decay of matter is uncertain. But in the search for proton decay, we may ultimately discover something even more profound: the boundless potential for human exploration, discovery, and understanding. As we continue to delve into the intricacies of proton decay, we uncover not just the physical and theoretical implications but also the deep philosophical questions it raises. What does it mean for something as fundamental as a proton, the very building block of matter, to decay? If the proton, once thought to be impervious to change, can eventually succumb to decay, what does that say about the stability of the universe itself? These questions challenge our understanding of the very nature of existence. The process of proton decay could be seen as a cosmic unraveling, a slow but inevitable process where the forces that bind matter together gradually weaken and break down. It's a stark reminder that even the most seemingly indestructible objects in the universe are not immune to the passage of time. But as we consider this possibility, we also have to ask ourselves, what happens next? If protons decay and the building blocks of matter vanish, what does the universe look like in its final stages? The decay of protons doesn't just imply the end of matter, it suggests that everything we know, the galaxies, the stars, even the very atoms that make up our bodies, could one day fade into nothingness. For many, this thought is a humbling one. It underscores the fragility of existence and the transient nature of all things. But it also opens up a fascinating line of inquiry. What might happen to the laws of physics as the universe undergoes such an eventual transformation? Would the principles of quantum mechanics, relativity, and thermodynamics still apply, or would they give way to new, unknown rules as the universe enters a final state of entropy? One possible outcome that some scientists speculate is that proton decay could be a contributing factor to the universe's eventual heat death, a scenario in which the universe reaches a state of maximum entropy, with all matter dispersed and all energy evenly spread out. In such a scenario, the universe would experience a slow and inexorable decline into a state where no work could be done, and all physical processes would cease. The heat death theory, which predicts a universe devoid of structure, is often seen as a natural endpoint for a universe governed by the second law of thermodynamics. The decay of protons would fit perfectly into this picture, as it marks a further breakdown of the material fabric of reality. However, even in this seemingly bleak scenario, there remains a sense of wonder and awe at the complexity of the universe. The journey from the Big Bang to proton decay is a story of cosmic evolution, a tale of formation, destruction, and transformation. And perhaps the most fascinating aspect of proton decay is that, even though it signals the end of matter as we know it, it also serves as a gateway to new possibilities. What might emerge in a universe devoid of protons and matter? Would the laws of physics themselves change in ways we can't yet comprehend? Perhaps the very nature of time and space could shift, and we could be looking at a new kind of cosmic existence. There are also theories that posit proton decay could play a role in the development of new structures in the universe. While proton decay would lead to the breakdown of traditional matter, it might also facilitate the creation of new types of particles or even entire realms of existence beyond our understanding. For example, some researchers propose that proton decay could lead to the emergence of dark matter or dark energy in ways that we can't yet detect. These mysterious substances are thought to make up a significant portion of the universe's mass, but their exact nature remains unknown. Proton decay could be one of the mechanisms that give rise to new forms of energy, allowing the universe to continue evolving in ways we are still trying to comprehend. The concept of proton decay also touches on the idea of time itself. As we mentioned earlier, the timescales involved in proton decay are so long that they challenge our very perception of the passage of time. A single proton's decay might take trillions upon trillions of years, far longer than the current age of the universe. In this sense, proton decay forces us to reconsider how we measure and understand time. If protons are, in fact, decaying at such an infinitesimally slow rate, what does that tell us about the other processes in the universe that we can observe on much shorter timescales? How much of the universe's history is hidden from our view, simply because it happens over such a long period of time? The slow decay of protons might also bring attention to the limitations of human perception. We are accustomed to thinking of time as linear and finite, but the possibility of proton decay forces us to confront the idea of an almost incomprehensible timeline. It asks us to imagine a future that stretches so far beyond our own understanding that it seems to defy the very notion of the end. And yet, in this cosmic perspective, the eventual death of protons may be just another chapter in a much larger story, one that we might never fully grasp, but which continues regardless. Additionally, the search for proton decay is a reminder of the power of human curiosity and the scientific endeavor. Even though we might never witness proton decay firsthand, the pursuit of knowledge in this area has already led to new insights into particle physics, quantum mechanics, and the fundamental forces that govern the universe. The search for proton decay pushes the boundaries of our understanding and expands our conception of what is possible. In this sense, it reflects the essence of scientific exploration, the willingness to ask difficult questions, to search for answers in places we can't yet reach, and to challenge our deepest assumptions about the universe. Moreover, the discovery or non-discovery of proton decay would have profound implications for our broader understanding of physics. If protons do decay, it would suggest that the standard model of particle physics, which has served as the cornerstone of our understanding of the fundamental forces of nature, might need to be revised. The current model assumes that protons are stable, and if it turns out that they are not, it could lead to a whole new set of theories to explain the forces that govern particle interactions. This would be a revolutionary shift in our understanding of the universe, one that would challenge our assumptions and open up new realms of inquiry. Proton decay is a concept that straddles the boundary between the known and the unknown. It challenges our perceptions of time, matter, and the universe itself, offering a glimpse into the distant future of the cosmos. While the search for proton decay may seem like a theoretical exercise, it speaks to deeper questions about the nature of existence and our place in the universe. Whether or not proton decay is ever observed, the very idea of it forces us to confront the limits of our knowledge and to consider the possibility that the universe, and everything within it, is subject to forces far beyond our comprehension. The search for proton decay is not just a scientific pursuit, it is a philosophical one as well. It invites us to reflect on the impermanence of all things, the fragility of matter, and the mysteries that lie beyond the reach of human understanding. And perhaps, in the end, the most important lesson of proton decay is that the universe is full of mysteries waiting to be uncovered, mysteries that may forever change the way we see the world around us. As we continue our journey into the theoretical implications of proton decay, we find ourselves at the crossroads of some of the most profound questions in modern physics. The deeper we delve into this hypothesis, the more it becomes clear that proton decay might not just be a process that signals the eventual end of matter but also a key to understanding the very laws that govern the universe. To think that such an elusive event might have the power to unravel the structure of reality itself is nothing short of mind-boggling. But what is the scientific basis for these ideas, and how are researchers approaching the challenge of detecting proton decay? The primary difficulty lies in the sheer timescale involved. To understand why proton decay is so challenging to observe, we first need to consider the strength of the forces that hold protons together. These forces are incredibly powerful, operating at distances smaller than an atom, and are governed by the strong nuclear force, one of the four fundamental forces of nature. The strong force binds quarks together to form protons and neutrons, and it is far stronger than both gravity and electromagnetism, making the proton exceptionally stable. Yet, even these powerful forces may not be immune to decay in the far distant future. The hypothesis that protons eventually decay, albeit at a rate that is currently unmeasurable, comes from theoretical work in the field of grand unified theories, GUTS. These theories attempt to unify the three fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single framework. According to Guts, the strong nuclear force that binds quarks inside protons and neutrons may be much weaker at extremely high energies, such as those that would have been present in the early universe. Over time, as the universe cools and particles lose energy, this force may weaken further, eventually allowing protons to decay into lighter particles, like positrons and neutral pions. But here's where it gets really interesting. The timescale on which this decay would occur is extraordinarily long. In fact, it is so long that scientists have yet to detect any evidence of proton decay despite decades of searching. This timescale, which is on the order of 10 to the power of 34 years, is far beyond the current age of the universe, which is only about 13.8 billion years. To put this in perspective, the timescale of proton decay is about 10 million times longer than the current age of the universe. So, while the theory suggests that proton decay could be an inevitable event in the far future, it is so rare and so slow that it has not been observed within the observable universe's lifetime. This creates a significant challenge for scientists who are attempting to prove or disprove the hypothesis. In order to detect proton decay, researchers would need to observe large amounts of matter over incredibly long periods of time, which is, of course, impractical. This has led scientists to come up with creative solutions to the problem, particularly by developing extremely sensitive experiments designed to detect the faintest signs of proton decay. One of the most prominent experiments currently underway is the search for proton decay in underground detectors, such as the Super Kamiokande experiment in Japan. Super Kamiokande is a massive water Cherenkov detector that sits 1,000 meters beneath the surface of the Earth in a former mine. The detector is designed to look for the rarest of events, including the decay of protons, by monitoring the interactions of particles that pass through the detector. The idea is that if a proton were to decay, it would release energy in the form of lighter particles that could be detected by the array of sensors within the detector. Although no proton decay events have been observed so far, the experiment has placed stringent limits on how quickly protons can decay, further refining our understanding of the timescale involved. Another experimental approach involves using the concept of a neutrino telescope. Neutrinos are incredibly elusive particles that interact very weakly with matter, making them difficult to detect. However, they are produced in enormous quantities in the Sun, in supernovae, and even in cosmic rays. Neutrino telescopes, like the IceCube Neutrino Observatory in Antarctica, are designed to detect the rare occasions when neutrinos interact with atoms in a detector. While these experiments are primarily focused on neutrino physics, they also provide valuable insights into the search for proton decay, as any new particles produced by proton decay might generate detectable signals in such detectors. Despite the lack of direct evidence for proton decay, there are other intriguing theoretical consequences that stem from the possibility that protons might eventually decay. If proton decay were to occur, it would not only lead to the breakdown of matter but could also have significant implications for the future of the universe itself. As protons decay, the atoms that make up stars, planets, and living beings would no longer be able to hold together. Over vast periods of time, the universe would gradually lose its material structure, leading to the disintegration of galaxies, stars, and even black holes. This is sometimes referred to as the Big Freeze, or heat death, of the universe, a scenario where everything eventually reaches a state of maximum entropy, and all processes grind to a halt. However, proton decay is not the only potential mechanism that could drive the universe toward this eventual state of heat death. The expansion of the universe itself plays a key role in this scenario. As the universe continues to expand, the energy within it becomes more and more spread out, leading to a decrease in the ability of particles to interact and form structures. This, combined with proton decay, could bring about a slow but inevitable decline of the universe as we know it. But there is another possibility. Rather than leading to complete dissolution, proton decay could open up entirely new realms of possibility. Some researchers have speculated that proton decay could create the conditions for the formation of dark matter or dark energy. These mysterious substances, which are thought to make up the majority of the universe's mass and energy, remain largely undetectable, but their influence can be observed through gravitational effects on visible matter. It's possible that proton decay, or some related process, could lead to the creation of new forms of matter and energy that we cannot yet detect. If this were the case, the decay of protons could be just one phase in a much larger cycle of cosmic evolution. Moreover, there are some ideas that suggest the very nature of space-time itself could change in response to the decay of protons. If matter breaks down, could it be replaced by something else, something entirely unknown to us? Could we eventually see the emergence of new forms of fundamental particles, or even entirely new dimensions of space and time? These are questions that scientists are only beginning to explore, and answers may not come for millions or even billions of years. But the potential for discovery is one of the most exciting aspects of this research. The idea of proton decay also forces us to think about the limits of human knowledge and understanding. If proton decay occurs over timescales that are so long that we will never be able to observe it directly, does that mean the end of our ability to understand the universe? In some ways, proton decay could be seen as a humbling reminder of the limits of human experience. We are creatures bound by time and space, but the universe itself operates on scales that are far beyond our comprehension. And yet, the fact that we can even theorize about such distant events speaks to the remarkable achievements of modern science. Through the lens of proton decay, we can glimpse the ultimate fate of the universe, even if that fate lies far beyond our grasp. The Proton Decay Hypothesis invites us to explore some of the deepest mysteries of the universe. It challenges our understanding of matter, time, and space, and raises profound questions about the future of the cosmos. Whether or not proton decay ever occurs in our lifetime, or at all, this concept forces us to confront the impermanence of existence and the transient nature of everything we know. The search for proton decay continues to push the boundaries of science, offering us a glimpse into the far future of the universe and the ultimate fate of all matter. As we continue to explore the profound implications of proton decay, it becomes increasingly evident that this concept has far-reaching consequences for our understanding of the universe. The potential end of matter, as we know it, introduces an entirely new realm of possibilities, one where even the most fundamental building blocks of nature could eventually disintegrate into nothingness. Yet, as we dig deeper into this hypothesis, we find ourselves at the intersection of both awe and uncertainty, faced with a cosmic puzzle that stretches across time itself. One of the central questions that arises when discussing proton decay is its relation to other cosmic phenomena, especially when considering the future of the universe. If protons, the essential components of all matter, were to eventually decay, how would this process align with the universe's continued expansion? Since protons are integral to the formation of atoms, and atoms are the building blocks of stars, planets, and all known matter, the gradual decay of protons could lead to a scenario in which the universe ceases to be a place where matter exists in its familiar form. Yet, despite the slow nature of this process, proton decay could ultimately signal the conclusion of the universe as a system of material substance. This is not the only theory that attempts to describe the distant future of the universe, however. Proton decay plays a key role in a broader theoretical framework that aims to predict the ultimate fate of the cosmos, sometimes referred to as cosmic fate theories. These theories often build upon established concepts like the Big Bang and cosmic inflation but take the concept of entropy and the eventual degradation of energy to the extreme. The end result of such theories is a universe devoid of organized structures, where all the galaxies, stars, and planets are gradually stretched and scattered into oblivion by the ever-expanding cosmic fabric. One of the most intriguing aspects of proton decay in this context is its potential to accelerate or intensify the universe's gradual decline into a state of maximum entropy, often referred to as heat death. Heat death is a state in which all matter and energy in the universe have reached an equilibrium. There is no more usable energy, and all particles are spread out so thinly that no significant interactions take place. However, while proton decay may contribute to this end, there are still uncertainties as to whether this process alone is enough to bring about heat death in a reasonable time frame. Interestingly, some cosmologists have speculated that proton decay might also be connected to what could be called dark energy, the mysterious force that is believed to be driving the accelerated expansion of the universe. While dark energy is still poorly understood, it is often linked to the idea that the universe's expansion will continue indefinitely, leading to a future where galaxies drift farther apart and stars burn out. Could proton decay be tied to this expansion, somehow contributing to the increasing dominance of dark energy? While this is still a topic of ongoing research, it introduces an interesting avenue for further exploration. Proton decay may not simply represent the final disintegration of matter, but a transformation of the very forces that govern the universe. The potential relationship between proton decay and the behavior of dark energy also raises the question: could proton decay be the key to unlocking the nature of dark matter and dark energy? These two mysterious components of the universe remain elusive, and while their effects are detectable through their gravitational influence, we have yet to directly observe or identify them. If proton decay is ultimately tied to the behavior of dark matter or dark energy, it could offer the missing link needed to understand these profound cosmic phenomena. The idea that proton decay, seemingly a mundane event at the atomic level, could be intricately connected to some of the largest and most enigmatic aspects of the universe is a tantalizing possibility that could redefine our approach to cosmology. This intersection of ideas brings us back to the question of whether proton decay could eventually lead to new forms of matter and energy. If protons do decay, could they give rise to particles or forces that we have yet to detect? Could this process, occurring over unimaginably long timescales, be the precursor to new and unknown types of matter, much as the early universe experienced a phase transition from one form of matter to another during the Big Bang? Some scientists propose that the decay of protons could lead to the creation of exotic particles or even new types of energy that could fundamentally alter the fabric of the universe. These potential discoveries would not only redefine our understanding of physics, but also could open the door to entirely new realms of exploration. As we contemplate the potential of proton decay to unlock the mysteries of dark matter, dark energy, and the fate of the universe, it is important to remember that we are working within the boundaries of what we know. Our current understanding of proton decay is theoretical, and much of it is based on models that are difficult to test in the short term. The experimental challenges associated with detecting proton decay are immense, but the value of this research lies in its ability to push the limits of what we understand about the universe. Whether or not we are able to observe proton decay in our lifetimes, the effort to explore this hypothesis will continue to shape the field of physics for generations to come. In many ways, proton decay is not just a scientific concept, it is a reflection of our deepest curiosity about the universe and our place within it. It forces us to confront the impermanence of all things, including the very building blocks of matter. As we continue to explore the cosmos, we may eventually uncover the hidden mechanisms behind proton decay and, in doing so, learn more about the fundamental processes that govern the universe. Whether we uncover the truth behind proton decay or not, the search for knowledge continues to propel us forward, guiding humanity toward new frontiers and deeper understandings of the universe. The possibility that protons, the very foundation of all matter, could eventually decay and cease to exist raises profound questions not only about the nature of the universe but also about the ultimate fate of everything we know. And yet, even as we grapple with the enormity of these questions, we are reminded of the limits of human understanding. Proton decay may be a process too slow to observe in our lifetimes, and the timescales involved may be beyond the comprehension of any living creature. But that doesn't make the idea any less fascinating, nor any less essential to our understanding of the cosmos. The story of proton decay is a story of time. It is a story about how the very fabric of the universe, from the smallest particles to the largest galaxies, is constantly changing and evolving. The potential decay of protons represents the slow, inexorable passage of time, a reminder that even the most stable and enduring components of the universe are not immune to decay. As we continue to search for the answer to this profound mystery, we are reminded of how little we truly know and how much more there is left to discover. And so, we find ourselves left with the tantalizing question: will proton decay truly mark the end of matter, or will it simply be the beginning of something entirely new? This question remains unanswered, but the search for the truth continues, inviting us to explore the farthest reaches of space and time. As we venture deeper into the concept of proton decay, we must begin to understand the mechanisms and scientific theories that support it. Proton decay is not just a curious idea, it's an integral part of certain grand unified theories, GUTS, in physics, which aim to explain the fundamental forces of nature in a unified framework. These theories attempt to bridge the gap between the four known forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. According to these theories, the strong nuclear force, which holds protons and neutrons together in the atomic nucleus, might not be as permanent as we once thought. The main theories of proton decay arise from attempts to unify the three forces, electromagnetic, weak, and strong, into a single, cohesive theory. One of the most famous of these theories is the Grand Unified Theory, GUT. The idea behind GUTS is that, at extremely high energies, like those that existed in the very early universe, these three forces were once one single force. However, as the universe cooled, this unified force split into the distinct forces we observe today. GUTS predict that under extreme conditions, such as those at very high temperatures or energy levels, protons may decay. However, the process of proton decay is incredibly slow, so much so that it is virtually impossible to detect in a human lifetime. In fact, the predicted lifespan of a proton before it decays is mind-boggling, on the order of years, far longer than the age of the universe itself, which is about 13.8 billion years old. While proton decay is theoretically possible according to GUTS, there is still no experimental evidence to support this hypothesis. In fact, the search for proton decay is one of the most challenging and exciting pursuits in particle physics. In order to detect proton decay, scientists need to observe extremely rare events, so rare, in fact, that they would occur only once in a vast number of protons. This is why many experiments focus on large detectors buried deep underground, in places like the Supercameo Candy detector in Japan, which is designed to capture rare particle interactions by shielding the detectors from cosmic rays and other forms of radiation. Despite decades of effort, no conclusive evidence of proton decay has been found. The absence of proton decay from these experiments has placed significant constraints on the predictions of GUTS, but it hasn't yet ruled them out entirely. In fact, the search for proton decay is ongoing, with scientists continually refining their models and testing new hypotheses. This persistence underscores just how central proton decay is to our understanding of the universe's most fundamental processes. Even without direct evidence of proton decay, the theoretical implications of its existence continue to shape our understanding of the universe. If protons do indeed decay, it would mean that the universe is not as stable as we once thought. The atoms that make up all of matter would eventually break apart, leading to the slow disappearance of the material world as we know it. In a universe where proton decay occurs, everything from stars to planets, to galaxies, would ultimately disintegrate over unimaginable timescales. Matter, as we understand it, would fade into nothingness, leaving behind a barren and empty universe. But what happens when protons decay? According to GUTS, the decay of a proton would result in the release of energy and the creation of new, lighter particles. These particles would be unlike the matter we are familiar with. Some scientists speculate that these particles could be exotic, possibly even related to the mysterious phenomena of dark matter or dark energy, which remains some of the biggest unsolved mysteries in modern physics. If proton decay does indeed lead to the production of such particles, it could fundamentally change our understanding of the universe's structure and the nature of reality itself. The concept of proton decay also invites questions about the very structure of space-time. In the absence of matter, space-time itself may undergo significant transformations. Could proton decay lead to a shift in the way space and time behave at the quantum level? Could new forces or fields emerge from the dissolution of matter, opening up new avenues for exploring the fundamental nature of the universe? These are questions that remain unanswered, and exploring them requires a deeper understanding of quantum mechanics and the laws of physics at the smallest scales. One aspect that makes proton decay particularly intriguing is its connection to the Big Bang Theory and the early universe. According to cosmological models, the universe began as a hot, dense point, expanding rapidly in a process known as cosmic inflation. During this early period, particles such as protons, neutrons, and electrons were created from high-energy interactions. The decay of protons, if it were to occur, might offer insights into what happened during those early moments after the Big Bang. Did the universe begin as a collection of unstable particles, and are we now witnessing the gradual transformation of matter into new, unknown forms? Proton decay also brings into focus the relationship between time and the fundamental forces that govern the universe. If protons are destined to decay, this means that matter is not a permanent feature of the universe. The implications of this are profound. Matter, which forms the basis for everything we experience, is ultimately impermanent. The eventual decay of protons would mark the end of all physical objects and structures, including stars, galaxies, and even black holes. In a universe governed by the inevitable decay of matter, all things would eventually fade into emptiness, leaving behind only the remnants of a once vibrant cosmos. Some physicists argue that the discovery of proton decay would not necessarily lead to the death of the universe, but rather to the birth of something new. In this view, proton decay could serve as the gateway to new forms of matter and energy. It could herald the beginning of a new phase in the evolution of the cosmos, one in which the traditional building blocks of matter are replaced by something entirely different. This idea fits into broader theories of cosmic rebirth, where the universe undergoes cycles of expansion, collapse, and transformation. At the heart of all these speculations is the idea that proton decay challenges our conventional notions of time and existence. In a universe governed by such slow, gradual processes, the fate of the cosmos seems both inevitable and unknowable. It raises the question, is the universe a truly transient entity, or is it merely undergoing a process of transformation that will lead to new and unforeseen possibilities? The ultimate answer remains elusive, but the quest to understand proton decay offers a fascinating glimpse into the mysteries of the universe. As we continue exploring the implications of proton decay, it's essential to acknowledge how it fits into the broader framework of theoretical physics. While proton decay is primarily discussed within the context of grand unified theories, GUTS, it also touches upon the deeper issues of time, entropy, and the ultimate fate of the universe. Understanding proton decay isn't just about predicting the end of matter, it's also about gaining insights into how the universe began and how it might continue to evolve. In terms of entropy, the decay of protons could symbolize the slow but steady progression towards a more disordered state in the universe. Entropy is the measure of disorder in a system, and the second law of thermodynamics tells us that, in any isolated system, entropy will always increase over time. As protons decay, it could be seen as the universe moving toward a state of maximal entropy, a state in which no useful energy remains, and everything has become uniformly disordered. This concept of a universe moving toward greater entropy ties into what some scientists describe as the heat death of the universe. The heat death is a theoretical scenario in which the universe has reached a state of thermodynamic equilibrium, where all processes that involve energy or work have come to an end. In such a universe, stars would have burned out, galaxies would be isolated, and even black holes would have evaporated. If proton decay is indeed a key factor in this process, it suggests that the universe's future will be marked by a long, slow fade into nothingness, where even the most fundamental building blocks of matter will eventually break down. But why would protons decay in the first place? And why would they do so at such an incredibly slow rate? These are the questions that physicists are still grappling with. The decay of a proton would involve the weak nuclear force, a force that typically governs processes like radioactive decay. However, the strong nuclear force, which holds protons together in atomic nuclei, is incredibly powerful, so breaking that bond requires an enormous amount of energy. In the context of GUTS, the theory posits that at extremely high energies, these forces could unify, and protons would become unstable. The result would be the eventual decay of protons over vast periods. One of the key predictions of GUTS regarding proton decay is that the decay would lead to the emission of lighter particles, such as positrons or neutrinos. These particles are known to be very difficult to detect, making the search for proton decay an incredibly challenging task for physicists. However, recent advancements in particle detection technology and experimental setups, like the aforementioned Super Cameo Candy detector, have made it possible to observe the interactions of subatomic particles with greater precision. While proton decay has yet to be detected, the constant improvement in these technologies keeps the hope alive that one day, we may uncover definitive evidence of this mysterious process. Another important aspect of proton decay is how it might tie into the fundamental symmetries of the universe. Symmetry is a central concept in modern physics. Many theories rely on the idea that the laws of nature are symmetric and consistent across space and time. For example, the law of conservation of energy asserts that energy cannot be created or destroyed, only transformed. Proton decay might violate this kind of symmetry in a fundamental way, challenging our understanding of how the universe operates on the most basic level. If protons can indeed decay into other particles, it would force us to rethink the nature of conservation laws and whether they are as inviolable as we once believed. Additionally, proton decay could have profound consequences for our understanding of dark matter and dark energy. Both of these mysterious phenomena make up the majority of the universe's mass and energy content, yet we have very little understanding of what they actually are. Some theories suggest that the particles produced by proton decay might be connected to dark matter, which would make this process a potential key to unlocking the mysteries of the unseen universe. In this sense, proton decay could provide a missing link in our quest to understand the true nature of the cosmos. Despite the theoretical support for proton decay within GUTS, some scientists question whether it will ever be possible to detect such an event. After all, the predicted lifespan of a proton before it decays is so long that it's almost beyond comprehension. If proton decay is real, we are talking about a timescale so vast that it stretches far beyond the reach of human observation. But even if we can't detect proton decay directly, its theoretical implications remain profound. It could be the key to understanding how the universe functions on the most fundamental level and how it might one day come to an end. One of the most fascinating aspects of proton decay is its connection to the concept of the final state of the universe. In cosmology, the final state is a theoretical scenario in which the universe has exhausted all of its available energy and matter, and nothing is left to sustain any physical processes. The decay of protons, in this context, would mark the final stage of this process. It would be a universe where nothing but diffuse radiation remains, a cold and dark place, completely devoid of any recognizable form of matter. In a sense, the idea of proton decay serves as a reminder of the impermanence of the universe. While stars and galaxies may shine brightly for billions of years, and matter may seem eternal, the eventual breakdown of protons shows that nothing in the universe is truly permanent. Over incomprehensible timescales, everything we know will be destroyed, broken down, and transformed into something new, or perhaps even into nothingness. This inevitable decay of protons also brings into question our own place in the universe. If everything is subject to decay, what does that say about the transient nature of life, of civilizations, and of everything we hold dear? Are we simply fleeting moments in the grand scheme of time, like the protons we are made of, slowly decaying until we, too, fade away? These are the kinds of existential questions that the study of proton decay invites us to ponder. Ultimately, the search for proton decay is not just a pursuit of knowledge about the ultimate fate of matter. It is also a quest to understand the universe's most fundamental processes. If we can unravel the mysteries of proton decay, we may uncover hidden truths about the very fabric of reality itself. Whether or not we ever detect proton decay, the implications of this idea will continue to shape our understanding of the universe and its future. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.